Info. Ja.
Oh, it seems everyone had too much drink yesterday. Good morning, everyone. Welcome to the first session of the last day of SQA. My name is Yin, and I'm a senior RF engineer at Skylink. I hope everyone enjoyed the conference, Gothenburg, the fantastic conference activities, and especially the weather, not today. As someone live here for more than 8 years, I promise you it's not like that every day. SQA is blessed by universe somehow. Today, I'm honored to introduce Professor Whitleaf Vyacherik from Chalmers University of Technology to talk about his exciting research on levitated microparticles that somehow behave with quantum effects. The floor is yours, Whitleaf.
Thanks a lot. Thanks a lot for the kind introduction. Thanks also for the honor to be a keynote speaker at SQA. It's the first time that I'm here, and I feel a bit uncomfortable because we don't have qubits yet in our research, but at least we use Josephson junctions. So I hope I can cater you a bit of the nonlinearities which you exploit for building, for example, a superconducting quantum computer, but we use it for something else. As we heard already, the weather in Gothenburg can be nice, then it looks like that. I think you have experienced it, but it can also be different. But anyway, it's a very nice city. So in the field, especially I think a lot of you try to scale up quantum systems to build hardware which can exploit that more qubits can do at some point algorithms or quantum simulations. This is not what we do in my lab. We try to do another way. Basically, we want to scale up the mass of the system. and look at the quantum behavior of such a massive object. So basically, what we are interested in is very simple. It's this. We want to have a massive object which can be placed in a superposition that is at two places at the same time. This has been done already, yeah. And you can look at this graph. There one can very nicely see what other people try to do and have done. So basically, if we have here on the y-axis the superposition size of such a macroscopic quantum state, and on the x-axis the mass of the system, there are different points in this plot. It's amazing experiments which have been done. For example, here, it's an atomic cloud which has been placed half a meter apart, yeah, in a quantum state. Admittedly, the superposition size was very large, but the mass of atoms is very, very small. Then we have this black spot, which was a recent work by Markus Arndt's group, where they started at some point with full arrays and do matter wave interferometry, basically classical double slit experiment type of experiments, but much more sophisticated. And now they managed to put nanoparticles in a quantum state. But still the mass is kind of smaller. So here we are basically on the left side, we are in the realm of atoms and molecules. And then we can go to the solid state where the density, obviously, of an object is much, much larger. And there are also fantastic experiments been done by the group of Andrew Cleland and recently by Yiwen Xu, where they placed basically these man-made objects. The laser point is hard to see, but you can believe me here, the man-made objects into superposition states. What we want to try to do is to go somewhere in between. So basically our target is to reach this mass regime and this superposition size, which people have not managed to do so. So the question is, why should we do this? An obvious thing is we want to do Schrödinger's cats, dead in the live objects. In our case, it's an object being here and there at the same time. And then it's basically, we want to extend the realm of quantum physics. So can we do this? Yeah. Can we as physicists or engineers control nature in such a way that we can isolate an object as much as possible from the environment, that one can see such a quantum state? Quantum mechanics tells us it's possible if we can control decoherence. Yeah, this obviously we have to minimize as much as possible, but there are ideas that there are effects outside of our current theory of quantum mechanics which prevent us from doing so. And this will basically falsify such ideas. They are called collapse models, yeah, if one manages to extend such object sizes. Then rather recently, but it has a long history, it may be a way how to probe in tabletop experiments the intersection between quantum mechanics and gravity. It sounds a bit crazy, yeah, because we talk now about microparticles. Obviously, they don't have a big gravitational field, but there are actually ideas that even this tiny gravitational force which can interact between microparticles can be used to infer if gravity can behave quantum mechanically or not. Obviously, we know gravity is a classical field theory, no quantum physics, no entanglement. Yeah? So if you could do such an experiment where gravity is used as a channel mediating entanglement, then you basically, probably you get a Nobel Prize, yeah, but that is probably 50 years away. Yeah, but there are a lot of ideas of new experiments one can do to test this intersection in the tabletop. More mundane, if you place an object into a superposition state, it's very sensitive. Yeah, I already mentioned decoherence to environmental effects. So it could be used as a sensor naturally. This is what we usually write in our grant applications, I guess. And here what I plot is basically the sensitivity to inertial forces. Yeah, it's basically measuring small g or an acceleration. And if I'm in this regime here, in this purple marked, okay, in the purple marked regime, I'm better than an instrument which you can buy nowadays. It's called the Superconducting Gravimeter. And if you're better than this instrument, what you could, for example, do is to detect earthquakes, not via seismic waves, but via gravity changes. And that would be fantastic, because then you can warn people about 10 seconds before the earthquake actually comes to you. Yeah? What you could also use then these instruments is for probing certain dark matter models or for complementary looking for gravitational waves in different frequency regimes. If you go to the other side, if you make this mass a bit smaller, and you somehow enter this green marked area in the sensitivity to measure forces, then you're in the regime where you can basically measure gravity between small objects and maybe look for what happens if you place a particle in a superposition state and it interacts gravitationally with another test particle. Yeah? But you have to reach this sensitivity at least. Yeah? On paper, it might be possible. Yeah? Okay, this is the motivation. What do we need in order to do these experiments? We need a massive object. This is clear. I already mentioned we need to isolate it as much as possible from the environment, yeah, from known decoherence mechanisms, and we need to have quantum limited readout and control. And in the following of my presentation, I will discuss all of these aspects. How we do it is we use magnetic levitation, also not new. Yeah? Basically, we are using a superconducting particle, microparticle, and place it in a certain magnetic field environment. In our case, there's a quadrupole field. Superconducting particles expel magnetic fields, so they are low field seekers, shielding currents built on the surface, and then they minimize their energy in a certain field environment. And this is basically how you can stably trap or levitate them in free space. So here it's shown as basically a coil-based trap, counter-propagating currents, and then you get a quadrupole field. And in principle, this does the job on paper. You can levitate objects which are very small, yeah, from the size or mass picogram, given basically that the object should be superconducting, so it should be larger than x times the London penetration depth. But you can levitate kilogram objects. That's in principle not a problem. Our fridge is too small for that, yeah, but in principle one can do it. You can very well isolate this object from the environment. First, it levitates, yeah, it's in free space. It's not connected to any mechanical support, to any chip. So you basically don't have energy loss by direct coupling to the environment. So the only mechanisms you have is basically black body radiation, yeah, which gives information about the position of the object, or gas particles hitting the object. But this is minimized because we operate at millikelvin temperatures. This is the best you can do with conventional technology. Yeah, you suppress black body radiation as much as you can. And at millikelvin temperatures, you're better, most probably, than ultra-high vacuum environment. It's actually not clear what's the pressure. And one can also efficiently read out and control such a levitated object using magnetic flux, but I come to this later on. So this is how our particles look like. Actually, these ones we do ourselves. That's why they are not really super perfect, but they are good enough. So we have particles which have the size of 50 micrometer. So it's a microgram in mass. These particles we currently use in our levitation experiments because they're easier to handle. Ultimately, we have to go to these small ones, 3 micrometer particles, and they weigh hundreds of picogram. We can use particles of different materials. This is actually lead, so a superconductor which has been used early on, then forgotten, and we like it actually very much. Yeah, but there are also other materials, tantalum, indium, aluminum, which all would be valuable to use. Then we place this particle in our magnetic traps. In our case, this quadrupole field we generate on a chip. So what you see here is basically a chip, 7 by 7 millimeter, which has basically implements 2 coils on top of each other, and we place a particle in a hole. Yeah, it's a bit, I hope you can see it. It's there, a 50 micrometer particle in a 120 micrometer diameter hole. And we have basically a lot of windings which make up the coil for generating the magnetic field to levitate on a chip. The magnetic field landscape looks like that. That's the top view of a simulated magnetic field distribution. The green area, or the green, signifies large magnetic fields. Yeah, we achieve fields in the order of tens of millitesla. And in the center of this picture, exactly, it's a bit bluish. There is basically the field minimum where the particle will levitate. This is the top view, the XY plane. In order to have stable levitation, I obviously have to have such a minimum in all three directions of space, but this is what we have. So if you look at the cross section from both sides, you see there and there also a field minimum. What you also see, because we do it on a chip, you see it a bit here. Obviously, the coil has to have openings, yeah, and this gives a kind of asymmetry in the trap. Yeah, this lifts basically the degeneracy in a perfect quadrupole trap. The trap frequency in the X and Y direction would be the same, but it's not in our case because we do it on a chip and have openings. Then an exciting question, I think, is what trap frequency can we achieve? Yeah. Not gigahertz, unfortunately. Yeah. So the trap frequency is basically given by the gradient of the magnetic field and the density of the material. The density of the material, I mean, we don't have a big handle on it. One can take lead, which is very dense, or a lighter material like aluminum. The trap frequency, we have some handle over, in our case, as we do it on a chip. So we can do microfabrication. So the distance between the coils, in our case here, it's 150 micrometer, very close. And then basically the amount of current gives us the gradient. Yeah? But typically we get trap frequencies of 150 hertz or 200 hertz. This is a frequency where it's not so much fun to do experimental physics, I can tell you. Yeah? But it works. Good. Then we have a particle, yeah, sitting in a chip. Yeah, you saw the picture. Basically, we load the particle at room temperature, and then one has to think a bit about the adhesion forces. When we put a particle on a chip, yeah, I mean, you have certain forces acting there, van der Waals force, or if you have some water, it's even worse. And one can roughly calculate what's the adhesion force of a particle, and this turns out to be 500 nanonewton. Yeah, doesn't sound like a big number. If you compare what's the force of gravity, yeah, that's a nanonewton of this object is basically nothing. It's negligible. Yeah, so surface forces rule for these small particles. And then the question is, if we were now to switch on a magnetic field, yeah, then a gradient would act, and the particle wants to go to the field minimum. What's the force we can generate, yeah, to lift the particle off? And it basically looks like that, right? The particle sits on the bottom initially. We switch the field on if it's superconducting, and it would go up. Yeah? And roughly the force is, or can be, 300 nanonewton. So you see there's a bit of a problem, right? This can be larger than this, and then the particle would not lift off. And as everything is in a cryostat, you cool down, doesn't work, warm up, a week is gone. Yeah? You do it again, a week is gone. So that's why we invested really some time into reducing adhesion and did some experiments to determine what's the force required to detach particles from a surface. What we use typically is a silicon chip. Then what you see here is basically what's the probability that the particles move if I apply this type of force. Yeah, you have basically in 1/3 of the cases, on average, a particle will move. It's a 50 micrometer diameter particle in this case. Then we can treat the surface with known treatments. Here, for example, it's HSQ. It's an E-beam resist. And there you already see that you gain nearly a factor of 2 in probability that the particles move. The best actually what you can do is Teflon. Yeah, here, very simple. You take Teflon tape and then you reduce the adhesion force even more. Yeah, this is how your frying pan works, right? It's Teflon coated. So what we now always do is we use HSQ because it's very thin. Yeah, in our clean room we don't have yet Teflon coating, but it's soon to come, and then we will switch this. Good. Then we are basically done. In our diffage, we have optical axis because we are actually not sure in the beginning if this experiment is working at all. Yeah, and then it's good to see if something is happening. And so we have an optical window. Then we place our chip-based trap inside. And then the experiment is very simple. You cool down to millikelvin temperatures, run current through your trap. Yeah, it's 0.5 ampere at millikelvin temperatures roughly, and it should levitate. Yeah. So, and then we look inside and what you see here. So basically, initially the particle rests on the surface and then it jumps. Yeah, then we switch on the current, and then after some time, so it moves a bit around. Yeah, it's the top view. Yeah, and then falls down again. We cannot see the motion out of axis because we look from the top. Interesting phenomenon, right? I mean, here you see levitation, then it falls down. This is not really desired because in principle, we want to do experiments over an extended amount of time, but it falls down because we look at it with optical light. Superconductors absorb light, you break Cooper pairs, at some point superconductivity breaks down, and then the particle falls. The good thing is, it's not shown here, the process is reversible. After some time, the particle thermalized again to millikelvin and actually levitates again. But the good thing is, when you optically look at it, you can do some image processing, and that's what we did. We can determine the position of the particle over time, and then take the Fourier transform, so we can look at the noise spectrum. And what we see there is then we get really the motion, the direction of the motion in the X and Y direction at the frequencies we would expect. Here it was around 50 Hertz. Then another surprising aspect is that the motional amplitude is on the order of micrometer. It's good because this you can see optically. Wavelength is roughly half a micrometer, so you can resolve this, but this is actually absolutely not expected. So the motion, what we roughly measured is micrometer. If you calculate how much thermal energy this corresponds to, of this motional amplitude, it's 10 to the 9 Kelvin. But as I said, we levitate in a Dirichlet. At 50 millikelvin, it should be 50 picometer. So there are orders of magnitude energy intake to the particle to explain this motion. And it's clear, because we use a Dirichlet, it has vibrations, and these vibrations give additional stochastic energy to the particle motion and basically heat the motional amplitude up. And if we measured actually our vibrations, and then we expect roughly an amount of 10 micrometer of motional amplitude. So this is something you don't want to have. I think in superconducting qubits, you don't care so far about vibrations, but maybe at some point you do care. And then what one can basically do is, our experiment, we basically rigidly connected so far to the mixing chamber plate, but this is actually not very elegant. So what one should do is basically, you hang the experiment on a kind of mass spring system. And then what happens basically, if you have, this system obviously has a resonance frequency, but above the resonance frequency, any external vibrational amplitude gets dampened. So it's a basic low-pass filter, you could say, mechanically implemented. This is what we did, self-made. So basically here you see one of our students, Marty, shaking our vibration isolation system. It's basically hanging from here, from the 4 Kelvin plate. It's some nylon wires, some springs, and here below we have basically our experiment. That also obviously prolongs the cooldown time. It's not, well, I mean, we thermalize here with copper braids, but everything takes longer than. We measure then also the transfer function. So it has some resonances here, which are close to the pulse tube, but not exactly at the pulse tube frequency. That one should obviously avoid. And then at the frequencies of interest, here it's 100 Hertz, we get roughly a suppression by more than a factor of 100. We are limited here by the sensor noise. It's actually not so easy to measure suppression of vibrations with the equipment one has. We soon get a better system, and then we hope that we get actually a factor of 10,000 to 100,000 suppression in vibrations. Good. Then I said we need quantum limited readout. That basically means if I assume that our particle thermalizes at base temperature, it would correspond to 10 to the 6 phonons, and average thermal energy measured in phonons. And basically, we have to bring it down to the ground state or close to the ground state. This one can do, in principle, using squids or squid resonators, and this is what I'm talking now about. Okay. So the basic mechanism how we can detect is like that. The particle always moves in X, Y, Z. That means because it's a superconductor in the Meissner state, it will always perturb the magnetic field distribution around it. And that means if you place a coil somewhere, you change the flux through the coil. Yeah. So motion of the particle changes magnetic field. This magnetic field change you can measure with a coil. Yeah, you measure flux. And then it's clear what to use. You use flux-sensitive elements, which are very, very sensitive detectors of flux changes. Then the question is what we have to achieve. In our world, we call it the quantum cooperativity, and the quantum cooperativity has to be larger than 1. This is basically the ratio of how fast you extract information from your system, so the measurement rate, compared to the thermal decoherence rate. Yeah. So basically, the thermal decoherence rate is incoherent information loss. Yeah. This you want to beat with having a very, very efficient measurement to acquire the information. This one can also quantify. The measurement rate is basically the rate how good your detector can resolve the 0-point motion of the particle. Yeah, this is what we want to achieve. We want to ground state cool, yeah, to 1 phonon or below. This is roughly 10 femtometer. Yeah, and basically the imposition noise of the detector has to be small enough in order to do this. And the thermal decoherence rate is given basically by the coupling to the environment. This is given by the phonon number and the dissipation rate of the system. Yeah. And if I put in some optimistic numbers, I get that our imposition noise floor of the detector must be better than 20 femtometer per square root hertz. Keep this number in your head, but it comes again. Good. Then the setup would look like that. We have the levitated particle here. Yeah, basically here that's the zoom in of our chip trap, an older version. The particle sits here inside. That are the trapping coils here, the white wiring. What we pattern as well on the chip is this pickup loop, which is integrated and sitting very close to the particle. And this is basically schematically shown here. It's basically an inductor, which via a flux transformer can transport the signal of the particle to some flux-sensitive elements. And so far we explore 2 options, either using a squid, yeah, which basically converts the flux into a measurable voltage, or a squid-terminated resonator, squid cavity or flux-tunable resonator, which basically converts the flux change into an inductance change into a change of the resonance frequency of the cavity or resonator. Let's look at the first mechanism. This we did. So basically we coupled our levitated particle via a flux transformer to a squid. We measure the voltage in real time, take the Fourier transform, and then you get a spectrum which looks like that, and where we can clearly identify the 3 motional degrees of freedom of our particle. So it's the motion in the x direction, in the y direction, and in the z direction at resonance frequencies which we expect. So we can do simulations of the trapping field, and that are basically the vertical lines, yeah, and the measured resonance frequencies are very close. So the deviation comes basically from the fact that our trap is not perfect. So basically the chips have a bit of misalignment, and this explains the small deviation here. So this lets us also now study the particle motion over time. So compared to optical levitation, where we could just levitate for some seconds, we can now levitate for days. Yeah, this is here more than a day of levitation. And here we plot basically the resonance frequency over time, and it's basically stable over this time frame. What you can also do is we can change the trap current on a chip, and this changes the magnetic field gradient, which changes the resonance frequency. And this you see here. Basically, it's the change of trap current, the change of resonance frequency, and here's the motion along the x, y, and z. And it should be a linear change, and this is also what we observe. Our current traps, actually, I don't have it on the slide, but there we improved basically the gradient such that we also have trap frequencies beyond 300 Hertz. Then a big question is, how good is the particle motion isolated from the environment? Yeah, that we also measure with the quality factor. And here it's basically a mechanical ring down. What we do, we excite the particle to a higher excited, to a higher motion and amplitude beyond It's vibrational excitation, and then we look how this amplitude decays over time. The axis is in hours, and basically it decays over some hours or 1 hour to its steady state, and this corresponds to a Q factor of 10 to the 6. In theory, it should be larger than 10 to the 10. It's obviously not. And one reason is that the material we use for this levitation is not lead, but lead tin. So it's basically a type 2 superconductor, which can trap flux. And trapping of flux is not so good because the flux lines, they will move, and then you have inbuilt dissipation in your particle. So it's clear what we have to do. We have to change the material and then see how this will behave in the future. Good. Then I want to come back to the noise floor in our detection. So the noise floor you basically see here. That's basically the baseline in our squid-based detection. It corresponds to an imprecision noise floor of 10 to the minus 8 meters. I said before we need 10 to the minus 14 meters. So it's 6 orders of magnitude difference. This can be explained basically by we have a certain transduction efficiency. So how efficiently can we measure or transport the flux change of the particle to the squid? That's given by this number. And then the squid has a certain intrinsic noise floor. Yeah, in our case, it was quite bad, I must say, 100 microfarad per square root of hertz. And this together determines the imprecision noise of the squid. So what one can do is now, one can look if one can improve on this figure of merit to get these 6 orders of magnitude. So one could imagine to improve the squid noise by a factor of 1000. And that means below microfarad. So the best squids in the world could do this. And improve the efficiency by a factor of 1000, which can be very hard. I mean, here in this experiment, I don't show it, but this connection was a 10 centimeter long twisted wire cable. That's not the optimal way how you transport flux from A to B. But it's basically very hard to do this. And that brought us to the question, can we do a more efficient readout? And yes, one can, by switching a squid to a squid resonator. And then the system would look like that. That basically we have here our trap, our levitated particle. Now I also write the Hamiltonian as a basic harmonic oscillator. We have here the superconducting circuit. It's in our case a squid resonator, whose if the flux changes, right, the inductance changes, and then the resonance frequency changes. It's a harmonic oscillator with an anharmonic term, weakly anharmonic term. And then one has a coupling between the two systems. In my world, I would call it radiation pressure coupling or optomechanical coupling, or it's longitudinal coupling, which is quantified by a coupling rate, which is tunable. This is a very good thing. So you can basically tune the frequency response of the superconducting resonator. And the rest of the coupling rate is given basically again by the efficiency of the flux transformer and the trap. The good thing about this system is you can boost the interaction by putting photons in a cavity. So basically via a drive, you basically displace your intracavity photon number with a mean field and fluctuations. And this mean field boosts here this coupling rate. This is very good. Good. How does it look in reality? So basically we have still our trap chip, the pickup loop, and now it's basically connected to a superconducting resonator, which is shown here. It's a basic transmission line, standard coplanar waveguide resonator, which is terminated here with a DC squid. In this image, I showed that we pattern the input coil, which basically transports the flux change from the trap to the circuit around the squid, and we used an air bridge. But we also have a flip chip implementation, but I don't show it here. Then the experiment looks like that. We have the trap chip here. Here we have the chip of the superconducting resonator. They are connected via these pins. The first experiment, what we did is basically we wanted to see if we can modulate our resonator. So we applied either external flux via a large bias coil, or we used the on-chip modulation with a DC current to see that we can tune. We can tune very nicely over 2 gigahertz. And then the experiment would be like that one parks the resonator at a certain flux bias point, which means it's sensitive to small changes. And then the particle would do a tiny modulation. Yeah, it's a lot overdriven here. Yeah. A tiny modulation in flux, which gives rise to a small frequency change. So we mimic this by simply applying an AC current here in the trap. And this is what we see. So we do homodyne detection on the superconducting circuit. We applied a modulation of 30 Hertz here at the trap, and we can see the signal there. Yeah. So it's basically working in principle. Unfortunately, that time the particle did not levitate. Yeah? So I cannot show you peaks here in the spectrum of a particle levitating. Yeah? But this is what we work on. That's next to be done. But what we can have a look at is the noise floor, what we expect now from this type of implementation. Yeah? Again, the imprecision noise, yeah, given for this type of readout is a bit different. It's given basically by the inverse of the measurement rate. And this is given by how strongly I couple the two systems, yeah, quantified by the coupling rate squared over the cavity degree and times the 0-point motion. So as I said, the good thing is this coupling strength between the two systems first is tunable. Yeah, I can park my FDR at a certain slope. Yeah. So I can change this, and I can also pump my resonator with a certain number of intercavity photons to boost this or to reduce the imprecision noise. Okay, let's put in some numbers. If I assume some reasonable numbers here for the first term, I would get an imprecision noise floor of 10 to the minus 11 meter per square root hertz per square root of photon number. That means in order to get 10 to the minus 14, I need 10 to the 7 intracavity photons. It's doable in principle, yeah, also with planar circuits. However, I said before, the resonator is nonlinear. So this is also what we see. Yeah, if we do spectroscopy of this flux tuner resonator and change the input power, it's shown here, that's the intercavity photon number, it shows basically spring softening or a Kerr nonlinearity. Yeah, and in our case, it's basically around 200 kilohertz. This is a killer. Yeah, it doesn't work. You cannot put 10 to the 7 photons in such a resonator. It's basically going to zero frequency. This is why what we currently do, we look into snails, where one can design a carefree point. We are aware of they also have higher orders, but basically we crunch now the theory and do also some fabrication in order to hopefully design resonators which are flux sensitive, but can carry a lot of photons. Yeah, to be seen. I think that's exciting because this is not what some people do usually in this field. Good. Let's assume we managed to ground state cool in 4 years or 5. Yeah. The next step would then be to generate really based on the ground state cool particle a non-classical state. And there one has different options to do so. One can couple it to a nonlinear quantum system, a qubit, yeah, a superconducting qubit, for example. One can do a projective measurement, for example, x squared. If you get an x squared measurement, you don't know if the particle was left or right. You're done. Or you put the particle into a nonlinear potential. And I want to show you just briefly how one can do a non-classical state with the latter approach. It's actually very elegant, so we like this very much. So what I've shown you so far is a quadrupole field. Yeah, this is very good for trapping a particle. We put it basically here inside, that's the field minimum, and the particle levitates happily ever after there. But magnetic fields can also have higher or lower orders. Yeah? So one can have a uniform field, a boring field, but one can also have a hexapole field. And the interesting thing is now if you combine these different fields, so for example, if I combine a uniform field and a hexapole, what I actually get is a field distribution with 2 minima. So either I can place 2 particles inside, or I can make a non-classical state. There basically is a double well potential. This is what we found after working together with a group in Barcelona. And then one can basically also imagine how to create these fields. Here it's again shown for a harmonic trap. It's counter-propagating coils, right, which create basically a harmonic potential along the z direction, which is here. If I now combine such a hexapole field, yeah, this is created with these 3 coils, and a uniform field, I can create a double well potential. Yeah. Or what I can also do, I can just take a hexapole field. For a small particle, it behaves like a Duffing potential. So basically a Z to the 4. And these latter two potentials can be used to generate non-classical states. I want to show how this looks like for the last part, for the Duffing potential. So the protocol would look like that. You ground state cool the particle's motion. Yeah, that's shown here. That's the Wigner function of the particle. So it's all theory. Yeah, no experiment yet. Not that you are surprised. Theory. This is the position. This is the momentum. It's not a squeeze state. Yeah, it's the ground state. We just had to scale the axis. Yeah, here that goes from -4 to 4, but basically the position as well. Yeah. So you cool the particle to the ground state or close to the ground state in a harmonic trap. Then you switch on hexapolar-like trap. So you see this a bit. So the trap weakens a lot, and on the outside it has nonlinearity. What you see immediately is that the wave function expands fast along the z direction. That means basically you get squeezing. Yeah? And then you expand it further in this trap. So you see here basically it expanded a lot in the z direction. Basically you generate squeezing. And then after some time, basically these wings of the wave packet experience the nonlinearity and they slow down compared to the center, and then you get interference fringes. So you get negative parts in the Wigner function. This you can continue, and then you basically get a spiral, and then you have these negative parts in the Wigner function, which tell you basically you're done, you have generated a non-classical state. If I look then at the position distribution, this is here the grayish line, I see fringes. Yeah, and this is something we would measure. We cannot do state tomography, that's, I think, impossible. But we can measure the position of the particle. And what we see is the probability of the position of the particle. The black line is if I had only classical physics acting. Yeah? And if I switch on my quantum dynamics, I see that I can generate fringes in this particle. This we would need to measure. Yeah? Then this is basically given how good you can resolve these fringes given by your measurement strength. Yeah, this we quantify here with a parameter chi. And you see that for low position resolution, you cannot resolve fringes. Yeah? And you have to increase your position resolution to a large chi. And that brings us again to a superconducting resonator with a lot of photons. Good. This will be hard, the experiment, because we need a Q of 10 to the 12. Yeah. So maybe we can talk again in 10 years about this. And I also wanted to do this. We also want to scale up from 1 particle to 2. Not 100 or 1,000. Yeah, but here basically we have a trap. That's a good thing if you work with chips. You can make a lot of holes. Yeah? So here I made basically 2 holes. It's 2 independent traps, yeah, which each can levitate a particle. The straightforward thing what we want to do is basically do differential sensing, because both particles would experience the same noise. Yeah, you can subtract the noise and can then detect a signal. In the long term, what we want to do is entangle the 2 particles with each other, yeah, and see if one can do this. But we won't scale to 1,000 particles, I can promise you. Good, let me summarize. So what I've shown you is that we can levitate superconducting microparticles on a chip. We integrate the readout with another chip. We can couple, in principle, to flux tunable superconducting elements. It will be a challenge, yeah, because one has to design the elements to our purposes. And in principle, one can also do multi-particle levitation. I think it's worthwhile pursuing these type of experiments. We are also not the only ones in the world who try this. There are different technologies how to address these questions. Yeah? So it's valid because we want to probe quantum mechanics in new parameter regimes. And one parameter regime is increasing the mass of the object. And if we have done so or designed these experiments, they are very sensitive to unknown physical phenomena like dark matter or detecting gravitational waves in different frequency ranges. Also, I'm not standing anymore in the clean room. Yeah, actually, I've never been. But therefore, I have a group, a fantastic group who made all this possible. Sometimes we also levitate. Yeah, actually here we were climbing in trees and luckily nobody fell down. Yeah, all survived, so we could continue with our experiments. We also collaborate with quite a lot of people and also get some money from some funding agencies which trust in our experiments. And I have to thank the team and I want to thank you for your attention.
Thanks a lot, Witlif, for your very interesting talk. Now it's time for questions. Oh, over there.
So I wonder about the rethermalization rate of your particle in your setup, or the thermal environment is probably quite hot or relative to your 150 hertz, even if it's at 30 millikelvin or so, and then there's probably also in your context also all the IR and so on that plagues superconducting circuits should also matter, and maybe even some high energy particles. So have you thought about that?
So rethermalization rate is basically given. Let's assume we thermalize at millikelvin temperatures. We get rid of the vibration and noise. Yeah. Then on paper, it's given by the phonon number of the particle times the dissipation rate. And the dissipation rate, one has to see where one basically lands in terms of quality factor. So right now, what one can expect is that there are gas particles hitting the particle, so normal gas around, but that should be actually zero. Yeah? And then the question is, what kind of mechanisms prevail? Is it flux trapping in the particle? Is it some flux trapping in the wire structures we have? Is it maybe some spins close to the chip surface, which basically give decoherence to the particle? IR radiation, I don't know. We haven't thought about this yet, but it's shielded. I mean, but it may be of an issue. I think we are too early to answer this question. Yeah, as you have seen, we need a quality factor of at least 10 to the 10 to the 10 to the 12. The experiments with magnetic levitation, which are similar, so far have 10 to the 6, 10 to the 7. But it's clear what to do next, and then one has to see where one lands. And all these mechanisms may be a limitation. Yes.
One last question.
Thank you for the nice talk. You spoke about the noise temperature of the particle induced by the vibrations of the fridge. How does it correlate with the other experimental parameters, like the particle mass or the drive current of the trap?
Yeah, I mean, obviously. So first, the vibration and noise has a certain background in frequency. Usually it scales 1 over omega squared. Yeah? So you can go to a higher frequency, and then the susceptibility to external vibrations depends then on the trap frequency, but also on the mass. So one can engineer this. Yeah? But ultimately, what I've shown you in the last slide, this quantum experiment we want to do, you need a 1 micrometer sized particle. Yeah? You cannot go larger. I mean, with this quality factor. So you're basically bound to this mass, and then we have to engineer our vibration isolation system that it works actually for this size and mass.
Let's thank Witlif again.
Thanks.
Yes. You can already start. Yeah. Okay. So good morning, everyone, and welcome to this fabrication and material session. My name is Irshad Ahmed, and I'm going to chair this session. And in this session, we have invited a speaker, Simon Lang from Fraunhofer EMFT, and he's going to discuss about CMOS-compatible superconducting qubits for scalable quantum computing. So it's Simon, you can start now.
Great. Thanks for the introduction, so I don't have to read the title on my own. And yes, my name is Simon. I'm from the Fraunhofer EMFT Munich. And first of all, it's quite an honor for me to be here and to start the fabrication section. I want to thank the committee for that. And yeah, my institute now focused in the last 4 years on fabricating superconducting qubits. And this essentially summarizes the core findings of my PhD thesis, which I also did with Fraunhofer in the past 4 years, and I finished successfully this year in June. So I can give you now the highlights in the next talk. So maybe in the beginning, we already heard now in the last 2 days a lot about algorithms and using a large amount of qubit arrays to do some nice calculations. But in the end, there's always a problem that you have to bring a huge amount of functional qubits together, and they also should have a nice T1 time in the end. So there's a really important paper. This is the guide on how to build quantum computing. And they showed that in the last years, the progress on connecting multiple qubits is only slowly increasing. However, I mean, physically, it would be possible to connect a huge amount of qubits, but in the end, they should have a really high T1 time, and this is the problem, which can essentially be seen here by the IBM qubit chip. They show that they have really high T1 times, and the average is even above 100 microseconds, but still there is a few qubits with have only single-digit T1 times. So also here, there's the problem that although you get like really high T1 times, there are still some qubits which limit in the end the overall qubit chip performance. And this is a major problem which also stressed John Martinez in the March meeting last year. And similarly, we also came up with our CMOS compatible approach. So we use now a different approach compared to the normally used lift-off approach everybody's kind of using, because we think that this more CMOS compatible approach is more reproducible, as it's already known in semiconductor industry for quite some time. And it's more scaling oriented. And that's great because we want to scale qubits. So to bring you all on the same page, I will shuffle over the fabrication process and really quickly. So first we do the sputtering of the metal on our silicon wafers. This is normal and standardized to all other fabrication processes. So we then structure the metal using optical lithography, then followed by a dry etch process. Here we use a chlorine-based etch because we use, of course, aluminum. Then we in situ use water plasma to strip the resist. So this is done to avoid the chlorine to corrode the aluminum. This is followed by an EKC, because in the end there will be a lot of resist residues which you really want to get rid of. And if you do this correctly, you can see that you end up with a really aluminum-free silicon surface, as well as a carbon and etch residue-free aluminum surface. So this is a great first metal layer structured. And the second layer, compared to now, there would be this lift-off process. We have to argon ion mill and to remove this native oxide from our surface because it's thicker than it should be. Then we oxidize in situ and cap it again. So this all is done in situ. And in the end, we have to structure the metal layer again. This chlorine-based dry etch is similar to the one before. And again, if we do this really elegantly, we can see that we remove all of the aluminum residues on the silicon as well on the top, as well as on the bottom aluminum layer. And you really end up to have thin aluminum oxide in between our bottom and top aluminum. So that's great. But at this point, we cannot stop because now we only have working junctions, but we also want to have a uniform process across the wafer because, as I said, we want to scale this process. So we have to pay a huge amount of attention to process control monitoring, especially focus on room temperature measurements because this allows us to have a fast process cycle with the fabrication. So therefore, we use our simple test chip design with 4 fixed frequency qubits and some test structures, and we put this chip with about 108 time across our full 200 millimeter wafer. So every time when I talk about wafer scale, I'm actually referring to an 8-inch wafer because in these last sessions I heard that wafer scale also refers to 4-inch, which is of course more common to research labs, but we are using these 8-inch wafers. So if you use these test structures here, we implemented test junctions to measure the resistance distribution and also shorts to measure the line and the area with distribution. Because in the end, as I mentioned before, we use oxidation argon ion milling to fabricate our junction. So both will influence in overall our junction's resistance distribution. And in this process, for example, I was able to achieve a really low resistance distribution with just 12.4%. So this is a junction with same area and the variation across the whole wafer. So it's actually quite a low value, I would say, and the yield with about 92.8% is also reaching like an industry standard yield. And now we want, of course, want to even further reduce this value. So now we have to understand, is this variation mainly resulting from contact area or from oxide barrier? Because both we have to tackle individually. So what we do is we measure these shorts, as I mentioned before. I measure the resistance distribution. It is about 5.3 and 8.9%. With the sheet resistance variation, we are able to calculate the line width variation, which is about 5.1 and 8.7, which brings us to the area variation of about 10.1%. So already from this 12.4%, 10.1 is resulting from the area variation. And this results to an oxide barrier variation of about 7.2. So this 10.1 is far higher than this oxide barrier, so it would be good to remove it. And it's obviously not, it's so high because we're using an I-line stepper. So this is optical lithography. This is important because these junctions are much larger than normal Josephson junction used in university processing. So here we have, for example, for our bottom layer, a 350 nanometer width of the junction, which is already approaching the limit. But we are now shifting to an E-beam stepper since the last year. So we hope to remove, to further shrink this 10.1% to even lower value. And this is great that we have some room to improve this process even further. Yeah, so now we have working Josephson junctions, and we also are able to improve the uniformity. But to have in the end functional qubits, we also have to improve the T1 time of all of the chips. And we mainly focusing on using resonators for loss mitigation, because this is a really nice way to access these material properties. So what we normally do, we put these resonator chips across our 8-inch wafer. Then we take the individual chips, cool them down in millikelvin, measure the dielectric loss. And as we know that the TLS-related dielectric loss is connected to the T1 time, we can already get a nice estimate for the T1 time of our qubits in the end. So in this short section, compared to we normally have an all aluminum process, I want to shovel over a bit the titanium nitride investigation, because titanium nitride is also an interesting material as a base metal for the qubit fabrication, because it's a ceramic. It should create less oxide on the surface. And also a subsequent talk is talking about titanium nitride, so she will probably have more to show about it. I just wanted to stress out here that we were interested in if the crystal orientation is actually more important than the edge process, or the other way around. So what's actually the dominant one for defining the overall dielectric loss of the resonator? Because especially in the last poster sessions, I saw a lot of investigations on optimizing thin films, but then just using one single edge recipe and then say, okay, that's the best dielectric loss I got. But actually, we should optimize both, of course. But which one has more influence? So I did this and I tried to end up with like two crystal orientations to have some parameter to vary. So I used here this tin 111 and 200, and we also created a film with a mixture of both. I verified this with XRD measurements, and I also had different TCs for these this three distinct films, which is kind of clear. And now we use these three films, and we used two different edges. So we used a high power edge and a low power edge. For the high power edge, we ended up with nice steep angles in the sidewall, but also over edged a bit into the silicon, because we had no selectivity at the edge stop. But for the low power edge, we were able to achieve a nice selectivity here. But however, we had a rough sidewall because it was a more chemically based edge, and this is normally what is the main result then. And on top of that, we also use two different strip temperatures, because as I mentioned before, we can strip the resist of the wafer in situ in our chamber system. So we can also vary between a high and a low temperature. So now we have a broad frame of parameters which we investigated. So here you see the different crystal orientations in blue and orange. And at the end, for using a low temperature and low power etching, ended up to have the lowest overall losses, which was quite interesting, because there's a lot of literature saying that having a steep angle is really important, but the steeper angle and the higher power did not achieve that well. It did not result in that small dielectric losses as you would have expected. Also, we saw that high power overall resulted in higher losses as well as high temperature stripping for both edges. And if you compare the different crystal orientations, we could see that they actually end up with quite the same amount of minimal dielectric losses, which was interesting. So having different crystal orientation is not actually having that high of an impact compared to the edge recipe, which has had like more than 2 or 3 orders of magnitude. So optimizing the edge recipe is really important. So now, as we already see that this high power edge introduced something on the edge surface which is having a higher loss, we thought about how can we remove it. And an obvious idea would be to use BOE, because BOE is known to remove silicon oxides as well as oxides on niobium and tantalum. You can also use it on titanium nitride. And we use now both mixed films, the high power and the low power etching. And we could see that starting from here, we could reduce the dielectric loss, and they actually end up to be comparable in the end. And if we apply a time coupling, so we etch the resonator and cool it down in 2 hours, then we even end up to be like close to or even beyond a million quality factor. So that's great. So this BOE treatment is really efficient to remove edge-induced surface losses. So that's also why I came up with the idea of using it, obviously, for our aluminum resonators, because they are in our qubit chip. And as I mentioned before, this water stripping resulted in a thicker oxide. Which we measured this because, for example, here, here's the native oxide growth of our aluminum. And if we apply this plasma oxide, we more than double the amount of oxide on our aluminum, on our silicon oxide, and similar things can be estimated for the aluminum oxide. So this should be, of course, removed for our process. And one obvious choice for the silicon oxide is HF vapor. This is already kind of a known method in semiconductor industry to remove sacrificial surface silicon oxides. So this is a selective process for silicon, aluminum oxide, and aluminum. Pay attention that this is here vapor HF and not liquid HF. There's a huge comparison. I will catch up later on that. And now it would be interesting is if there's something similar for aluminum oxide, because this is still here and we couldn't remove it. And actually there is. So I used the aluminum wet etch, which is a standard recipe for in our lab. And this is a cyclic process. It uses nitric acid to oxidize aluminum and then phosphoric acid to etch the aluminum oxide away. So together they etch aluminum, but if I now remove the nitric acid and just use this phosphoric acid, theoretically, it should be possible to just etch aluminum oxide away. And that's great because the aluminum etch is also selective to silicon oxide and aluminum, so perfect fit. So now I can apply both of them on our reference sample. And we can see that using phosphoric acid as well as HF vapor both reduced the dielectric loss again by a factor of 3 to approaching a million quality factor. And applying both of them sequentially even reduced the factor of 9. And the TLS-related quality factor was here about 2.6 million. So this is quite high for aluminum resonators, just by removing selectively the surface oxides. And to better compare it with others, I also put it in this combined plot here. You can find the papers for the referenced chips here in the paper I published already beginning of this year. And our chip here aligns quite nicely with the previous data. And compared to what others are normally doing, they are using this liquid HF. And liquid HF is of course possible. You remove silicon oxide, you remove aluminum oxide, but the problem is that you have not that selectivity to aluminum. So we'll always etch a bit into aluminum. And I can assume that maybe this is happening here, because if you do it too long, you will etch into the aluminum, and that's why I do not see this improvement anymore. So compared to that, our process with this high selectivity, we had a process window of about 1 minute. So this is great because if you think about you want to dip a full 200 millimeter wafer, you need some time to insert it in and take it out. And having just 50 seconds of etching time is not sufficient. So we have really created a process with the selectivity to have a huge process window for our wafer scale fabrication. Yeah. So this brings me already to the last section of my talk, the qubit fabrication. Because, of course, in the end, the most important thing is for us to fabricate qubits. So all of the different investigations on a resonator is all summed up for our qubit fabrication in the end. We use this standard test chip, as I mentioned before, with these 4 fixed frequency qubits. And what we do is we, to benchmark for the full process or for the full wafer, we randomly pick chips across our wafer, across the full wafer, but only chips which are working, of course, so which are not shorts or open. And we do this because we do the resistance measurements before. So now we can see the distribution here, and we were able in the previous process runs to optimize our process. So we optimized here the etching process, and we could see that now the median and mean value are approaching 100 microseconds. So that's great. But some of you probably already see that there looks like a saturation, but this saturation we believe is resulting from using, or more from having a Purcell filter, a Purcell limit on our qubits, which was about 130 to 150 microseconds. So this is the first chip I used for my investigations. Now we updated the design with a higher Purcell limit, and we are pursuing and continuing our fabrication with this one. This should lift this limit here, and we can constantly improve the T1 time. Yeah, additionally to these investigations, we also wanted to see if our qubits actually apply to the Ambigaroka-Borato formula. So we plotted here the resistances of our qubits against the qubit frequency. We used the chips of the first 3 fabrication runs. And we can see that when we fit the values and we only have TC as a free fit parameter, we end up to have a TC of about 0.71 Kelvin, which is lower than we would expect for aluminium, which is about 1.2 Kelvin. But if you measure the Schwarz, which we have on our test junctions, we can see on our test structures, we can see that this is about 0.8 Kelvin. So the value, I mean, I'm not exactly sure why the value is lower, but at least the fit value resembles the measurement value. This is great. So this allows us to pick or we can selectively target qubits by measuring the room temperature resistance. And this brings me already to the end of my talk. I demonstrated you a CMOS compatible manufacturing process on 2D qubits. With our statistical process control, we were able to achieve this high yields with about 93%. And the resistance variation for this showed case was about 12.4%. Overall, the selective oxide etching also ended up with this really nice qubit-related TLS losses, quality-related TLS losses to be about 2.6 million. And our fabrication is heading to be about 100 microseconds in wafer mean. At the really last slide, because now there's a good thing for you, because we actually sell these processes, because we at Fraunhofer EMFT, we have a foundry service. So we do not only have this CMOS compatible qubit fabrication, but we also use TSVs and indium bumps for 3D integration. So we also have 3D integrated qubits. My colleague Carla showed it yesterday in her poster, she showed our 150 microseconds qubits with indium bumps, but we also have cables and 4K electronics. So if you're interested, just get in contact with us and we can set something up. And that brings me already to the end of my talk. So I want to thank, of course, my colleagues at Fraunhofer EMFT, also my supervisor for the chance for the PhD thesis, and of course the committee for the talk, and you for your attention.
Yes, let's thanks Simon for the nice talk, and we have a time for some short questions, 1 or 2.
Thank you. Is that working? Oh yeah, cool. Did you attempt to quantify the junction losses at all? Because they can be quite significant. Like you mentioned the Purcell losses are quite significant, and I believe that, but there's kind of a missing piece.
Yeah, so we tried to compare our qubits with the current lift-off technique. If this is, because it was a bit of a hard task to quantify the TLS density of our junctions. So we at least started with just comparing, and this is actually an excellent question because I have a backup slide, but I don't know if I can access it easily.
I think we can go quickly.
Yeah. So here, a colleague of mine, Shoki, he made a little test. We compared the T1 time distribution of when you measure long time T1 times, or the median value against the distribution, and we see that at least our chips align with the lift-off qubits. So for like qubits with about 300 microseconds, they are at least now comparable in T1 time. So they're not better yet. We are working on that, but at least for the last years, we achieved at least that we are comparable with current lift-off processes.
Yes, thanks. So one last question from Andreas.
So is the yield a per junction yield or a per device yield for your 6 qubits? Or what does it do?
You mean with yield, how many junctions are working for on
I
a chip?
mean, you quoted the yield. I
Oh
don't
yeah,
know
the
what you
yield
mean.
is for the full wafer. So we have about on every of these test chips, so this 108 test chips, we have about 4 test junctions, so 4 times 108, and this is the yield of them working. So these were like 92.3% of them were working.
Of the chips, not the junctions. Because if it was per junction or so, and you were making a device that has 300 junctions or so, then the overall yield would be not that big, or not many of them work.
Yeah, but we have also areas where we have more junctions on it, but the yields are comparable. But I don't have the values right now. But
I'll ask you later.
Yeah.
Let's thank Simmons for the nice talk. Yeah. So our next speaker is Sunmi Kim from National Institute of Information and Communication Technology, Japan, and she's going to talk about high coherence all nitride epitaxial superconducting qubits. So it's Alcia.
Thank you for the introduction. It's great pleasure to be here. Okay, so my name is Sunmi Kim from NICT in Japan. I'm happy to be here, and I would like to thanks to giving me a chance to present our recent work here. Okay, so as you know, for 30 years, superconducting qubits coherence time is very much improved. And I just extended recent work, and it goes to millisecond lifetime due to recent advancement in material fabrication and microwave engineering, as you know. And the recent material improvement usually based on base electrode and this substrate. So best data comes from tantalum electron and on the silicon substrate. So, however, although overall losses are reduced, the coherence from amorphous tunnel barrier of Josephson junction still remain a critical challenge. So, motivated this work. So, okay, so I'm sorry. So to solve this problem, architectural growth is very useful, as reported by these two groups. So when they use amorphous tunnel barrier, they could observe this kind of anti-crossing, and this is due to the TLS in the oxide material. And by using architectural growth of alumina on epitaxial rhenium film, they can reduce TLS and fewer anti-corrosive numbers. So this gives information that epitaxial growth can resolve two critical bottleneck of Josephson junction. So one is we can reduce TLS induced decoherence, and another one is we can unlock CMOS scalable manufacturing. So motivated by this story, we are concentrate on developing all nitride superconducting qubit. So basically, Josephson junction forms by niobium nitride and aluminum nitride, and it can be architecturally grown on substrate. And also there is several advantages. Niobium nitride has a higher critical temperature and larger superconducting gap compared to aluminum, one order higher. So we can reduce effectively quasi-particle excitation. Also, it is known that it has higher critical magnetic field over 10 Tesla. So this is very attractive for use as a quantum sensor under high magnetic field. So for example, for searching dark matter. And this allow us to form architectural tunnel barriers. So it is good for reducing TLS and also give a benefit for scaling. So, but when we use this aluminum nitride tunnel barrier, we have to be very careful about their structure because when aluminum nitride grow in the form of a habitational structure. It gives piezoelectric effect, and this is really induce strong decoherence by phonon emission. So to avoid this problem, we can utilize the cubic phase of aluminum nitride, and this can be realized by cubic structure of niobium nitride film. So this is very important thing. And the previous report shows very short coherence time when we use amorphous aluminum nitride. So coherence time is several tens nanosecond. But when we use epitaxial aluminum nitride tunnel barrier, it can improve it up to 500 nanosecond, but that is really limited by dielectric loss of MgO substrate. So to improve this, we employ the silicon substrate, and this actually, by domain matching epitaxy, we can epitaxially grow on titanium nitride buffer layer on silicon, and also this niobium nitride based tri-layer. So using this material film, we fabricated qubit by this process. So first we prepare silicon, which has high resistivity, more than 20 kilo ohm, and we deposit titanium nitride and the tri-layer, and we pattern Josephson junction and resonator, and we deposit silicon oxide as a sacrificial layer, and we do planarization by CMP process. And we make a beer hole, and we pattern wiring layer, and finally we remove whole silicon oxide by BHF etching. So after that, we just check IV characteristic, and we can confirm there is no difference between without and with BHF etching, because there is no oxide tunnel barrier. So recently, we demonstrated all nitride C shunt flux qubit, which has coherence time 16 microsecond. But we want to go further, so we recently focused on transmon structure. So epitaxial transmons we call the epimon. So we fabricate this kind of epimon as shown in this figure. So base electrode is titanium nitride, and the Josephson junction part is shown in this same image. As you can see, pillar type, very thin Josephson junction. And we utilize new sample package, which has your optimized cavity design and 3-layer low loss PCB, which is designed by Noguchi Lab in Tokyo University. So I just put two sample. Actually, both titanium nitride electrode has a titanium nitride electrode, but one is Josephson junction, aluminum-based Josephson junction, and the other is epimon. And the aluminum-based Josephson junction has a T1 like 524, and the center mean T1 is 330. But our epimon T1 is just around 570, but their center T1 is around 523. As you can see, the standard deviation is just 4% of mean T1, which is very narrow and very stable, which is measured for 40 hours. And with some other sample go more than 1 millisecond. This is unpublished paper, so I just show only very short data. But anyway, the quality factor is like 18 million, and we are entering millisecond era for nitride-based qubit. And let me summarize my talk. So we established all nitride fabrication technique on silicon substrate toward the new era of all nitride qubit hardware. And we demonstrated high coherence epimon, which has qubit quality factor 18 million. And as your future vision, we can scale up by leveraging standard semiconductor process a process for large-scale multi-layer process, and it can unlock new physics by harnessing the potential for high frequency, high temperature, and high magnetic operation. Thank you for, I would like to thank to all my collaborators, and thank you for your attention.
Thanks, Sunmi, for the nice, interesting results. And now we have a time for quick questions.
Hello. Thank you for a very nice talk. And I noticed that your transmon has a very long T1 compared to the previous flux qubit. So is it because of the improvement on the design, or you also have improvement on fabrication?
Yeah, both. So what is that? Previously, I used niobium nitride electrode, which has a lower quality factor, internal quality factor. And this titanium nitride has higher internal quality factor. And also qubit design, yeah, it has a parcel filter. We referred the Aalto University design, and this is very good. Yeah, and also sample package can be one of them. Or also careful filtering and shielding, also important thing.
Yes. So let's thanks once again, Sunmi. We have one more question. Sorry, we have one small question.
Hi. You said you had to grow the cubic phase of aluminum nitride to make sure it doesn't grow in a hexagonal structure for the piezoelectric effect. How did you do that?
Oh, so yeah, that is very important to avoid the piezoelectric property by sputtering, actually. Okay. Yeah. For detailed story, you can find the Terraisang's paper, but we can conform hexagonal structure from XRD when niobium nitride has 200 oriented structure. We think that is hexagonal structure, but when we grow this aluminum nitride thicker than 4 nanometer, it gives 111 peak that is related to the hexagonal structure. Yeah, and how to make that can be. You can just check this second paper that I applied physics express 2026 paper.
Let's thanks once again, Sunmi. Yeah.
Thank you.
And our next speaker is Sebastian from National Physical Laboratory, UK, and he is going to talk about imaging material defects in live superconducting circuits. and he is going to talk about uniformity and reproducibility of wafer-scale superconducting qubit fabrication.
Hello, everyone. Today I'm here to present you a bit about my PhD project, which is the uniformity and reproducibility of wafer-scale superconducting qubit fabrication. And I work at the University of Sherbrooke in Canada, and mostly in ETH, which is an academical research lab. So at the beginning of my PhD in 2023, you need to know that we had completely no experiences in qubit fabrication. So my actual supervisor had a lot of ambition for this because he wants to create a reference qubit for the future development in ETH. Duplicate this on a 200 millimeters wafer scale and do the whole wafer characterization at room temperature and cryo-1, and create a robust PDK that we can transfer to a CMOS industry, and also create the first foundry in Canada between the ETH and a C2MI, which is a research industrial lab for quantum application intended for academia. So at this point of the talk, we just want to actually catch up with the literature really, instead of going with crazy number of T1 and T2. So why do we want to go over 200 millimeters wafer? So the animation didn't work, unfortunately, but we want to do that to, as we know, the qubit have errors, bit flip, phase flip, but to avoid that, we need 1,000 of them to mitigate the error and put auxiliary qubits to correct this error in real time. So we really need to size up the process to be able to fabricate this 1,000 of qubits. And the other one issue with that is usually because right now we saw that qubits can be really really not non-variable in T1, but usually the T1 average time moved a lot during the experimental measurement. Like we can see here, we almost have a factor 10 between the minus and the max of the T1. So that's an issue for the error correcting code, because this code used the average T1, T2, and fidelity in their code, and we want to reduce this variation to be more effective on the error correction code. So that's why we want to fabricate over 200 millimeters wafer. By using this, that allows us to use the CMOS infrastructure, so we have access to industrial grade process, so better homogeneity, better reproducibility. So the whole goal of this project is really to reduce the spread of the qubit quantum properties across the wafer. So first, we really need to create reference superconducting qubits in the ETH. And we start with that for the qubit fabrication process in niobium for the ground plane and aluminum-based junction. It's a lift-off process at the beginning, because we really want to start with what is better for the qubit in the beginning. That was the lift-off process. And in the future, we're going to move to the etching recipe. So first, the qubit fabrication process is quite simple. It's really like the literature wants. You start by cleaning your wafer, do the NB deposition, also do the whole lithography process, etch your niobium, cleaning, and do your shadow evaporation Manhattan style. So that's pretty much basic stuff. But in 2 years of work, we get the first 2D superconducting of the University of Sherbrooke with pretty good result, actually, for the first time, which is we have a T1 and T2 of around 35 microseconds and a fidelity of state 0 of 90% and of the one state of 85%. So that was a huge achievement for us, because we are a team of 3 and we work on everything. So that was really a good result for us. And with that, we can really start to work on the transition to 200 millimeters wafer. So at the beginning, we didn't have any machine to code for the 200 millimeters wafer. So of course, we had a lot of variation in the resist thickness across the wafer. And we had, like, a few months ago, a new semi-automatic coder who came to work with us on that. And during these few months, we improve the non-uniformity across the wafer from 12% to 2.3%. So now we can really go more deeply into the fabrication process of the Josephson junction, because with the liftoff, the only critical part is really the resist. So we do have fabricate a whole wafer, many actually, wafer full of Josephson junction. And so we need to characterize them every 2500 of them. And this is 100 by 100 nanometers junction. So it's quite variable. So we already have a semi-automatic probe station that's allow us to really measure every junction. So we have a yield of 90% already. And but as you can see, we have a lot of variation inside across the wafer. But we can see that we have radial dependence from the center, and we have a bit of a linear shift in all the wafer. So on top of that, we have an automatic SEM that allows us to take SEM picture of all the junction. It's really helpful on the night. You have like your all 2500 junction characterized, and that's allow us to really see the size of the junction, so you can see that we have a radial dependence also and a linear one. But the real useful of that is when you combine both. By the relation here, you can extract the GC, and the GC, you have like your real dependence of your resist with the area of the junction. So that's allow us to tell that we have, as I said, a radial dependence position, a linear dependence across the wafer, which is set by the evaporation angle. So that's why we need to work more on the resist pattern. And we have a variation of GC that's correlated with the pump position inside the chamber. So we need to also correct that to be able to fabricate better qubits. So in conclusion, we're catching up with the literature for the first time. We did fabricate 2D superconducting qubits. We have installation of all the equipment for the 200 millimeters fabrication. We fabricate and characterized a full wafer of junction. So the next step are going to be using the data of the 200 millimeters to develop a geometric correction code. That's like this. The size of the junction is going to be moving according to their position on the wafer. And with that, we're going to be able to fabricate qubits on 200 millimeters wafer and characterize them, and then develop etching junction. Like this, we can compare the spread of the quantum properties across the 200 millimeters wafer for the two fabrication method. So thank you very much for your attention.
Yes, thanks a lot for the nice presentation. And we have a time for one quick question. Yeah. Just we'll give it. You can take anyone.
Hi. Hey. Hi, thanks for your talk. On one of the slides, you showed that there's a huge amount of qubits open, and this was the
at the center, yeah.
So
it was
can
because that was a fab issue, or more human issue actually, because my colleague actually who was fabricated this exact sample, like blow on the center of the wafer with the gun hazard, so that's really erased all the junction at this exact point. So that's the issue here.
Okay, let's thanks once again. And we have our next speaker is Kaveh from University of Glasgow, UK. And he's going to discuss about reconfigurable superconducting metamaterial for scalable quantum computing.
Hello, everybody. Welcome to this session on unconventional qubits and principles beyond computing. This is very exciting because now we can actually get back to our roots, thinking a little bit more about physics. We got a little bit of an introduction today with Whitleff this morning. So without any further ado, I'd like to introduce our first speaker, Daniela Gove from the Weizmann Institute of Technology.
Thank you. It's very exciting to be opening the miscellaneous session of the conference. We're going to switch gears a little bit, and today I will be discussing a very fundamental aspect of observed quantum systems. I'll show you what actually happens when you gradually open Schrödinger's box, and by that I mean turning up how strongly you observe a quantum system. So let's begin. Or not. Okay, I got it. So when we consider the Schrödinger box thought experiment, the two limits are textbook physics, right? So on one hand, we have a closed box, and we have a cat that we can push in and out of a superposition by driving it. And it evolves deterministically under the Schrödinger equation, so no surprises here. On the other end, however, when we have a completely open box and we observe the cat, it collapses to one of the classically permitted outcomes. So in this case, the cat is alive. But the question of this talk is, well, quantum mechanics can come with an extra knob, that is, how this lid can be maybe open gradually. What would happen to the cat then? And I want to ask, as you turn this knob, is the road between these two limits smooth, or does it have some sharp transitions? And the answer is there's sharp transitions, which theory predicts, and we have observed them. Our system is composed of two transmons in a rectangular readout cavity. So a very, very simple system. We have one transmon here shown in red, which is aligned with the cavity field lines. So it interacts with it via dispersive shift, while the other transmon, the dark transmon, is perpendicular. So no dispersive interaction. So the first one, the red one, we will call the detector transmon, and the second one is the system transmon. Together, we get a V-shaped level system. So we have one joint ground state and two excited states, one for each of the transmons. And we can, of course, drive both of these transitions, the system 0-1 manifold with drive, which we denote by omega S, and the detector drive, omega B. And we can continuously read out the state of the B population, so whether or not we're at the B state. The net effect is that of a two-level system weakly coupled to a detector. So we have a detector coupled to the ground state, and it clicks with some probability whenever we're in the ground state at rate alpha. To the more theoretically inclined folks in the audience, this corresponds to a non-Hermitian effective Hamiltonian. So even if we don't get any clicks, we still have information coming, because the more time we don't see anything, the more likely we are to be at the excited state. So our knob here is the unitless measurement strength lambda, and it's nothing but the ratio between these two rates, the detector, the click rate, and the Rabi rate. Now this is the heaviest slide of the talk, so bear with me. I will now show you what theory predicts, so what transition we expect to see as we sweep this parameter lambda. And what you see at the top panel here is the no-click trajectory. So we look at what happens to the dynamics when we don't see any clicks. So every now and then a click happens, and you can see it maybe as these dark gray bars at the top panel that resets to the ground state. But we ask how the evolution looks like in between clicks. And turns out that at the beginning, when we have really weak measurement, we see oscillations. But as we turn up this measurement strength, these oscillations completely disappear. And in the ideal case, this is also associated with a forbidden region on the Bloch sphere. So we have an entire set of angles that we no longer have access to. And this is the first transition, which we denote by the quantum jump transition. As for the second transition, now we turn to look at the dwell time. So we ask how much time on average we spend at each angle on the Bloch sphere. And turns out that as you increase the measurement strength, at a certain point, this time diverges. So we spend a lot of time at a specific angle before resetting back to a ground state by a click. And this is the second transition, which we denote by the state freezing transition. Last but not least, now we turn to look at the average ensemble dynamics. So we're no longer interested in the no-click trajectory, but rather at the average dynamics. So we no longer care when a click happens, we just average the trajectory. And we see that at a certain point, the oscillations disappear even in the average case. And if it rings a bell, that's because that's the quantum Zeno effect. So the third transition is the quantum Zeno effect. So we have 3 transitions with 1 knob. Let's see them. So here what you see is the measurement of the post-selected. So we do a tomography in real time. Post-selected, I'm not seeing any clicks. And we measured the excited state probability. And we indeed see that at a certain measurement strength, we no longer see oscillations, they completely disappear. And we measure that to be at lambda equals 0.99. This is the quantum jump. Now the second transition, I remind you, now we're looking at the dwell time. So what you see here are Bloch sphere cuts. The blue dots are the no-click trajectory. So we start at the excited state. And then, for example, for very weak measurement strength, we start oscillating inside the sphere. But we also check how long we spend at each angle, and this is the histograms on the Bloch sphere that you see. And indeed, at a certain point, this time diverges. In order to pinpoint when it happens, we fit this to a scaling model with some scaling exponent psi. Whenever this exponent is negative, this is when we have a divergence. So we find this divergence to be at lambda equals 0.95. And this is the state freezing transition. Now we're going to talk about the last transition, the quantum Zeno. And as I mentioned before, here what we're looking at is the average ensemble dynamics. So you see here different different ensemble averages for different measurement strength. And indeed, as we turn up the measurement strength, the oscillations in the average dynamic disappear. We can fit this and extract the oscillation frequency and the decay rate. And we find a transition where the oscillations go to 0. So this will be at lambda equals 1.09. And you can also see another hallmark of the quantum Zeno effect, which is beyond that point, beyond the quantum Zeno transition, the stronger you measure, the slower the decay rate. So you actually slow down the dynamics. This is the quantum Zeno. So indeed, we see the 3 transitions, but you may have noticed a quite bizarre feature, which is the state freezing transition happens actually before the quantum jump. And turns out that if you take into account experimental imperfection and specifically dephasing, and you do the actual computation, you see that these 2 transitions swap places. And it means that to some extent, the mere existence of the transition is robust. And we have managed to observe this swapping of transitions. So to sum up what we saw so far, the quantum to classical crossover is a cascade of dynamical transitions. It's not smooth. Decoherence can change the order of the transitions. And we can observe all 3 of them in one device, in one superconducting device. Now, a natural question might be, well, is that all? Do you expect to see more transition as you increase the measurement strength? And the answer is yes, we do. Turns out that if you look at the click statistics, which I have not shown, you can find hidden transitions which have topological properties. So stay tuned, because this is our next project. Here's the QR code to our preprint. I'll be happy to take any questions if we have time. Thank you.
Great. Thank you very much, Danielle. We have time for some questions, if anybody has any. Oh, right in the front here. Do we have somebody with a microphone?
Thank you for the nice talk. I know many co-authors personally. So what was experimental way to control lambda? This typically given by capacitances. So how we did on the experiment?
So lambda, so you have two ways to control lambda experimentally. It is dictated by the rate of clicks divided by the system drive. So you can either control the system drive to change it, the Rabi rate. This will change lambda. Or and this is what we do, change the bright transmon, the detector transmon drive. So this is our knob. This is how we change it. We fix omega S and we scan over omega B. And by that, we tune lambda.
Great. I think we have time for some more questions. I have one, actually. So it's a common feature that we've kind of realized in the superconducting community about mistype events and things. I was wondering if there's a relationship between kind of the weakness of the drive increasing. It's follow-up work, I guess, that you're doing, starting to look at as you increase the drive strength that you see more and more transitions. If you can see a connection between the mistype events that we're seeing due to the level nature of the transmon, measurement-induced state transitions. Yeah, and the work that you're going to be following up with. I saw maybe a few figures of it in your archive paper, but I was wondering if you could maybe have some comments on this.
So I'm not sure about the measurement-induced phase I mean, obviously this is induced phase transitions. And so what figure were you referring to?
I think it was in one of the appendices where you started increasing the drive strength and you started seeing more of these transitions starting to appear. Maybe I'm having it confused with some other thing that I saw on a poster.
So, okay, so we didn't have a poster today, but so indeed we do expect more transitions, but we did not show them in this work as they require a different type of analysis in which you don't do any post-selection at all and you only look at the statistics of the click, but this we haven't shown yet.
Great. With that, let's thank Danielle again. Our next speaker is Alessandro Catano from University of Milan Bicocca. And here he'll be talking about a 3-transmon shared squid architecture for analog quantum simulations.
Okay. Hi, everybody. My name is Alessandro Cattaneo. I'm a PhD student at the University of Milan Bicocca. And as you introduced today, I will talk to you about this 3-transmon shared squid architecture for analog quantum simulations. So I divided the talk in this way, so I'll go through the introduction now. So how can we realize a quantum simulation where the standard approach is through a digital simulation, where basically we decompose our simulation into a sequence of single and 2-qubit gates. This is in general a universal approach, which means that with a long enough sequence, we are able to simulate every type of system. Although the problem is that in this NISQ era, if the sequence is too long, and this typically happens for more complicated systems, then amount of noise that we get at the end of the simulations doesn't allow us to get useful results. A different approach is instead analog simulations. In this case, the hardware is optimized to simulate a specific physical problem. And in this way, we can minimize the number of operations. The drawback is, of course, that the required, a specific problem require a specific hardware, and so it's not universal. And an example where the complexity of the system is limiting the number of results that can be obtained with a fully digital simulation is the simulation of neutrino flavor oscillation in high-density neutrino environments, like inside supernovas. In this case, the Hamiltonian is composed by two terms, a single body part, which is easy to simulate even on a classical machine, and a neutrino-neutrino interaction, which is quite complicated due to the fact that it's an all-to-all interaction with tunable coefficients, which means that each pair of qubits in the system need to talk. And then the type of interaction is composed by this sum of products of Pauli matrices. And people have tried to simulate the system on an IBM machine in 2021, and they highlighted the limitation of the results due to the noise in the system. And for this reason, we started thinking about a device that could have been applied to simulate the system using this analog approach. And we came up with this idea where we have this three Trasmon architecture in red, orange, and yellow, and a central coupler in blue in the middle. And the main difference compared to like standard architecture is the fact that each junction of the qubit is not connected to ground directly as in normal architectures, but is connected to the inode of this squid at the center. And this force each currents of the qubits to pass through the same element, creating what is sometimes called as current coupling. Effectively, this is just an inductive coupling between the modes of the system, which has the property of creating a stronger hybridization between the modes. And this is in general a feature that we want because this allows us to achieve higher order and stronger interaction. And the way we can achieve interaction with such a system is exploiting the parametric interactions. So a parametric interaction basically is a specific interaction activated by sending a specific acetone to the flux-sensitive element. And now I will just go through a couple of mathematical passages to understand a bit better where it does come from, and basically what are the features in our device that we have to look at to achieve the interaction that we want. So one typically starts from the Hamiltonian of the squid and expand that, considering that the external flux is a sum of a pump contribution, which is our acetone, and a static bias, which is the typical static bias that you apply in a squid. And so you end to this form. Now, if we expand only the first part, we need first to expand the sign squid phase operator, and this brings us to this term here, which is just containing all the two-body contributions in the system. And between all these operators, we are going to choose only one, applying a specific frequency at the system. And we have this argument that in the rotating wave approximations, we can basically write the effective Hamiltonian as a single operator Hamiltonian. In this case, for example, I'm pumping at the frequency which corresponds to the energy difference between the 100 state and the 010 state. And so I'm basically activating the swap Hamiltonian between qubit 1 and qubit 2. Similarly, with the second term, we would get similar results, but in this case, thanks to the power of 3 at this exponent, we would end up with these free-body interactions. And a couple of comments regarding these slides is the fact that to achieve this free-body interaction, we need in general an asymmetric squid. And the most important part is that the strength that we can achieve in this way depends on the mode mixing, which is indeed referring back to the strong hybridization that we have in our system. And finally, the the coefficients here, which are the coupling coefficients, are tunable, and they can be changed, the strength can be changed varying the pump amplitude, which is in general a feature that we want to simulate our system. And now that we have all these ingredients, we proposed a scheme to simulate this system on such an architecture. So basically, our approach is to decompose the simulations into a sequence of single qubit gates and this central analog block gate where we exploit the all-to-all connectivity of our system. And in our architecture, this analog block can be just serialized applying 3 pump tones that are activating the swap interaction between each qubit pair. And we did some numerics, and we estimated that the circuit complexity for this algorithm is scaling as the power of 2 in growing the number of qubits compared to the power of 3 in a fully digital approach. And now I will present you the first results. So we realized the device, and this is the picture. So we have three transmon pads in red, orange, and yellow, and the coupler element in the middle. And in green at the bottom, I have the flux line, which is the one which is used to carry the tones. If we zoom in, the coupler is just this very tiny cross-shaped island whose extremities are connected to the qubit pads with the junctions. And at the bottom, we have the squid. If we zoom in on the squid, we can notice these tiny filaments in the middle, which is just a way to exploit the kinetic inductance to increase the coupling between the flux line and the squid, indeed. And the first good results we were able to achieve with this device is the following. So here I'm showing on the y-axis the energy of the 100 state, so the first qubit, and on the x-axis I'm varying the pump frequency. And as you can see, there are 3 avoided crossing which are created exactly at 3 pump frequencies, corresponding to the fact that we are activating the interaction in the first picture between qubit 1 and qubit 2, in the second picture qubit 1 and qubit 3, and the third picture is for a free body interaction. So in this case, we are basically realizing the interaction between the 100 state and the 011 state. And another results we're able to get out from this device is that we achieve the frequencies like comparable to what we are expecting. We found out that the anharmonicities were lower compared to simulation values, and this is something we are working on. But the most disappointing part was the fact that coherence is pretty low, like in the order of 1 microsecond. And we think that this might be related to the strong coupling between the flux line and our system, which is creating a sort of parcel effect of the qubit modes out of the system. And with this, I conclude. So we started with the problem, so simulating these neutrino flavor oscillations, and we propose an architecture which could exploit this different approach called analog quantum simulations. We propose an algorithm that could be run on this architecture. And finally, we did our first experiment where we observed that we can create parametric interactions, although there are still things to be adjusted, like, for example, low harmonicities and low T1s. And with this, I conclude. I thank you for your attention, and I'd like to thank my collaborator as well from the University of Milano Bicocca and the University of Waterloo. Thank you.
Thank you very much, Alessandro. We have time for some questions, if anybody has anybody. No? I actually have one. With the parametric driving, you always tend to have the higher harmonics getting generated when you start to drive to high powers. How high do you actually have to drive to see these effects, I guess, on these systems, especially since you're applying 3 drives simultaneously?
Yeah, so we haven't tried yet the parametric drive simultaneous, but yeah, that's a nice point, especially for our low anharmonicities. That's something that we have to take care of course.
Do you see any effects of leakage or anything already at this point?
Like, no, because at the moment the number of measurements we did are only showing like are not highlighting any of these leakage effects. Yes.
Do we have any other questions? If not, let's thank Alessandro again. Our next speaker is Isaac Dingfeldt from Chalmers University of Technology. Here, he'll be talking about Floquet-driven transmons as a simulator for interacting bosons and anionic lattices.
Yes, hello everyone. So I will be presenting a work that I've done alongside with my co-workers Laura, Jorge and Göran, all of Chalmers. And this is a work on quantum analog simulation. And luckily for me, our last presenter had a very nice introduction on this, because I only planned on saying that analog simulation is when you have some target system that you want to simulate with some controllable source system that can be effectively described by your target system. So in our work, we are using a grid of transmons. So our source system is then this Hamiltonian here, which is the familiar transmon Hamiltonian. It's an anharmonic oscillator. And what we require is that each of the transmon qubit frequencies can be driven in this manner. So it's a first order harmonic drive, and we want to have access to specific drive parameters. So the amplitude, the frequency, and the phase needs to be targeted in a quite a specific manner. So the first of our two target models is then the typical Bose-Hubbard model. And as you can see, these two Hamiltonians are quite similar. And therefore, this has been a popular simulation Hamiltonian for the transmon systems. The on-site interaction of the Bose-Hubbard model, which governs essentially the many-body physics of the system, is typically given by the anharmonicity of the transmons. The issue is that this is quite large compared to the capacitive coupling, so we're stuck in the strongly interacting regime, which is not necessarily where most of the interesting many-body physics happen. So the first of our two contributions is a proposal to get a tunable on-site interactions by driving the transmon frequencies for 3 bosons per site, which is then an extension beyond the current best method, which has 2 per system, whereas we have no inherent system limit. Secondly, we will also be targeting the more exotic anion Hubbard model, which describes anions in a 1D array. And again, it's quite similar, but as you can see, the hopping term has this density-dependent phase, which is the statistical phase of the anions. And here we can again tune the on-site interaction and the statistical phase theta. So let's see how this works. I will not be going through the analytical details. I will instead try to give you an intuitive picture of how this method works. So when you're driving the qubits in this harmonic manner, you get something called frequency sidebands. This is the most equations you will see. So when you take the hopping operator, AI dagger AJ, and you go into this interaction-like picture, you get a couple of things. So first you have this transition energy, which is the energy difference between the coupled modes. And then you also have these exponentiated sinus things, which is the integral of the cosinus from the drive. And these can be expanded into this Fourier-like series. So here we have this k omega I, which is then the sidebands of this frequency. And we can draw them out in this nice manner with these parallel lines that are integerally spaced in terms of this drive frequency. The width of each sideband is called the sideband amplitude, and this is given by the Bessel function of the corresponding order, which you can sort of think of as a Fourier coefficient. Okay, so how do we use this? So we can also rewrite the hopping operator into a term, a sum of Fock state transitions. And each Fock state transition will have a different transition energy. So if we set the static energies equal and we look at this 1, 0, 0, 1 transition, which is essentially the swap operator, the transition energy is 0. But still we're driving, so we have these sidebands, and the transition amplitude will be wherever 2 sidebands match. Then there are a resonant exchange of population between these 2 states, and the total transition amplitude is then the sum of all of these sideband amplitudes. And by tuning the drive parameters, we can tune the sideband amplitudes and effectively set the transition amplitude. We can also look at these higher occupied transitions, and then you would have a transition energy of alpha, the anharmonicity of the transmon. But once we start driving with sidebands, we actually get a smaller effective energy difference between the -1 and 0 sideband in this example, which then sets our effective on-site interaction. So this now effectively becomes the transition energy between these two states. And so by choosing the drive frequency, we can set the on-site interaction of the system. So the rest of the game is to numerically find the parameters which gives us the desired properties. This is quite straightforward if it's only one transition, but we need to recover the entire operator and have the same on-site interaction for the entire system. So we need to do it for all transitions simultaneously and equally. Now there are infinitely many of these, so it's impossible. So that's why we have to restrict ourselves to an excitation manifold. So we have here 3 particles per site, which gives us 9 of these Fock-state lattice transitions with 5 unique energies. And using some tricks, we can actually tune all of these simultaneously and equally. So we end up getting this effective Hamiltonian, which is essentially the Bose-Hubbard model, but now we have a tunable U. So let's see how this works in practice. So here I have initialized 12 sites in a 2D grid, where each of the 2 corners have 2 bosons each, which corresponds to setting the transmon in the Ket2 state. And on the y-axis, I have the time evolution of the system. The x-axis is the sites, and then the color is essentially the population of each site. So here we can compare it to our driven transmon system, where I've chosen the parameters to match this specific on-site interaction. And as you can see, we're able to reproduce the dynamics of this system quite accurately. There's nothing special with 10J. We can do 3, 0. We can do arbitrary on-site interaction. And across these ranges, we're able to simulate these systems then. And as I said, we can have up to 3 particles per site. So I also initialize this triplon in the middle state. And again, the left is the exact model, and the right is then the driven transmons with the particular choice of drive parameters. And then, as I promised, something about anyons. So we can also start driving with phases. So we can offset the different harmonics of the qubit frequencies. And then the sideband amplitudes, instead of being these nice parallel lines, we get something like this signpost here. So the different lines will start to destructively interfere. And what we end up getting is transition-specific phases. So here you can see that the 2011 and 1102 transition has a phase that's not shared by the other transition. So this is a density-dependent transition. Looking again then at the Anion-Hubbard model, we can see that we have this density-dependent phase here. Now, these 2 systems are not equivalent, but they are close enough that we felt encouraged to see if we could make them equivalent. And indeed, if this transition phase is a linear ramp in this statistical anion phase, these 2 systems are equivalent up to some diagonal rotated frame. So we simulated this as well. So here's the non-interacting case. The U is 0. And by only changing the statistical phase of the anion system, you can see how the dynamics changes. And we're able to reproduce this across the different values. More interestingly, when we turn on the on-site interaction, we get this characteristic asymmetric quantum walk. So as you can see, this initialized state, it's drifting to the right. It prefers one of the sides, which is a typical anionic behavior. And we can quantify this. So we can calculate the number of particles to the right of the middle and the particles to the left of the middle and do this sort of weighted difference. And when we do this for a range of on-site interactions and a range of statistical phases, we do indeed capture this asymmetry by simply choosing the correct transmon parameters. We have a validation of simulating a very anionic type of behavior. Okay, so to summarize, by tuning the individual transition between Fock states, we're able to simulate these both Hubbard-like models with a tunable on-site interaction by simply choosing the correct drive parameters. And by adding phases, we get these complex transition rates, and then we can simulate the anionic Hubbard models in one dimension. And finally, I would like to say, stay tuned for the archive preprint, which should be coming out in the next couple of weeks, hopefully. And if you have any questions, here's my email address. Thank you.
Great, thank you, Isak. Do we have any questions from the audience?
Thank you for the nice talk. So I have two questions. So typically, so in this nonlinear Hamiltonian of a Transman, this Hubbard term is actually negative, right? Was it ever important in your case? So you could simulate like Hubbard model with attraction, not repulsion.
So I was a bit, the on-site interaction will have the same sign as the anharmonicity.
Yes, yes, but it is negative for Transmans, yes.
Yes, so it will be negative here as well.
Okay, good. And then second question, typically if you think about real experiment, all these couplings, charging energies, they will be random. So you will never be able to probably to make a simulator where your coupling constants are the same over the lattice, since it is analog simulator. So it will be analog devices, random couplings. So dynamics will be completely different.
For sure, and you will always have some sort of, I mean, now this is a simulation, so it's quite exact, but as soon as you start doing more realistic parameter values, it becomes less and less exact. But I think an important aspect of analog simulations is not whether you can reproduce the exact dynamics in some, but you need to recapture some phenomena. And I think sort of playing around with the values, these sort of like capturing the asymmetry of this quantum walk, you can still have quite a bit of like leeway in the difference in your parameter values and still sort of have a good enough simulator. But I mean, the more exact you can have them, the better the simulator would be. And this is just a experimental truth that we have to deal with.
Great, thank you very much, Isak. Let's give him a hand once again. Our next speaker is Muhammad Ali Amir, and he will be presenting his work on Floquet-driven, or on real-time detection of correlated quasi-particle tunneling events in multi-qubit superconducting devices. Or, yes, always-on, highly efficient microwave photodetectors based on a superconducting artificial molecule.
Hello. Hi, I'm Amir Muhammad Ali, and I'm a staff scientist at Chalmers. And I would like to begin by thanking the organizers for this excellent conference and actually letting me speak about our recent work that came on arXiv a few days ago. So this work was done in what we call the 22Q lab, which is a lab here at Chalmers led by Simone Gasparinetti. And the work that I will show you today was actually executed by our brilliant PhD student, Vyom Kulkarni, who I had a privilege to supervise alongside Simone. So this is in the context of radiation field detection at single photon level. So before superconducting circuits, we actually learned a lot about the quantum nature of light by experiments in quantum optics, where a vital device was a photodetector, which worked at a single photon level. But this is really problematic with microwave frequencies because the photon energies over there is about 5 orders of magnitude lesser. So of course, what we do is actually field quadrature detection to detect these microwave fields. And we have really come a long way in this, especially with the help of near quantum limited parametric amplifiers, with which we can do single shots, measurements, and actually reproduce some of those quantum optics experiments. However, this still does not sometimes answer a very basic question, which is, for example, when has a single photon actually arrived, even though we can detect the fields really accurately. So where would that be important? So that would be really relevant in measuring weak incoherent radiation, where, for example, a spin system could be fluorescing and emitting photons spontaneously. And that's where a photodetector would be very useful. And also, for example, in photon clicks-based protocols in quantum information processing, where you could herald entanglement based on those clicks of photons. And also even in axion search and the dark matter research is somewhere where they really need photodetectors. So this is what motivates us to work on this. So superconducting qubits have actually made enormous progress in microwave photodetection, and I will briefly mention two different approaches. So one is to actually map the arrival of a photon on the qubit phase, where it flips the phase, or the other approach is when you map the photons on the state of the qubit. Now, these have actually achieved really high efficiencies. However, there's an issue that only cyclic detection has been demonstrated, which means that there's a period over which you detect or you acquire the photon, and then you have to stop and do readout and reset the qubit before you can do that again. And what we really wanted to go about is to build an always-on detector. So before I jump into that system, I would just like to review quickly how we do efficient photon absorption in a Lambda system. So this is a Lambda system where you have the topmost level, basically, which could decay into the two lower levels. And when you shine a photon onto it, there are three processes that are possible. So the first process is that it just reflects without any excitation. Or the second process, process B, is that it actually drives the transition from G to E, which then again decays back and re-emits that photon. And the third process is where it goes up to E and then decays through the other channel into state M, and then finally to state G. Now, it turns out that the processes A and B actually interfere destructively to the point that if these two decay rates, gamma EG and gamma EM, are actually almost equal, then you basically cancel them out completely. So that it's only the process C that actually remains. And there, what happens is that when you shine a photon, it absorbs it to state E and then ends up in state M. And if that is a metastable state, then you can detect that. So this is, the question is, how do we realize with superconducting circuits? So here is how we implement this. We have two transforms coupled to each other, which we like to call an artificial molecule with symmetric and antisymmetric modes. And we have a special trick in which we couple waveguides in such a way that the antisymmetric mode of the molecule couples to one waveguide and the symmetric mode couples to the other waveguide. And this actually symmetry selective coupling is actually valid also for the excited states, higher excited states. So this is how we design our photodetector. So here we have the antisymmetric mode over here and the symmetric mode. And we have a waveguide which basically receives the photons from a collection waveguide. And the antisymmetric mode is coupled to a coplanar waveguide resonator so that you can do readouts. And we have this photon transferred via a driven dissipative process. So we have a pump driving between S and the 2- state, which is in the second excitation manifold. So this is basically an effective driven Lambda system, so that when you have the right pump tune-up, this will basically have an efficient Lambda system absorption of the photon. So this is how we first test out if we can absorb the photon. So with a very basic VNA measurement on the waveguide, blue waveguide. So we begin with very low power and look at what reflects. So we have a lot of reflection at low pump powers. So most of it is getting reflected. But as we increase the pump power, there comes a point where the reflection drops to zero at a certain frequencies. And that is when we have basically nothing getting reflected, and we interpret that as the excitation getting transferred into the state A, which is supposed to be long-lived. And if you increase the pump power any further, we basically find Otler-Townes style splitting. So now we move on to pulse measurement for microwave photodetection. So here we begin with having a very long pump pulse on the antisymmetric mode. And then on the symmetric waveguide, we basically send out a weak coherent tone, which is shaped into a Gaussian pulse. So this is where we actually we control the number of mean photon number, which is represented by n bar. And then we do readout, which is in single shot readout measurements. So with n bar equal to 0, we find some amount of excitation in the state A, which we attribute to dark counts. On the other hand, when we go to some slightly higher n bar, we see a decent population in state A. So now that is how we basically measured the population of state A through these single shot measurements. And that population as a function of pulse photon occupation has this shape where it increases linearly in the beginning before it saturates. It saturates when n bar is a bit higher than 1, because then you are actually populating the higher Fock states, which basically will not be registered by our measurement because our device can only absorb one photon at a time. So when we zoom into a lower photon occupation, we find that the efficiency is about 73%. And this basically is the first step towards going for a continuous microwave photodetection, for which we would basically send out that pump tone continuously, send out a weak coherent tone, weak incident photon also continuously, and do the readout continuously. So with that, this is what a single shot measurement readout looks like. So we have this ticks over here, which we can distinguish between ground state and excited state of the state A. So when we look at a plot of those jumps, especially the jump rate upwards as a function of photon flux, we find the efficiencies of the is about 47%. And if we look at this efficiency as a function of the measurement rate, we find something that we understand. So at low measurement rates, basically with a weak readout tone, the SNR is quite weak, so the efficiency is poor. But as we increase the measurement rate to higher values, we also see that efficiency goes down, mainly because that is basically having a measurement back action on the symmetric state, so it's dephasing it, and as a result, the detection is poorer. So right in the middle, we find a maximum, which is about 47%. So in summary, we demonstrated the microwave photodetector design based on a 2-transmon molecule with a cyclic detection of about 73%, continuous detection of about 47%. And I didn't say much about the dark count, but that's about 1.3 kilohertz, which we find from the intercept on this plot. And we find that to be mostly limited by the thermal occupation of the symmetric waveguide when there is no, when we are not sending any photon. And we plan to use this for some of our experiments in quantum thermodynamics in the lab. And if you would like to think about any more application, we would like to hear from you too. Thank you.
Great. Thank you very much, Ali. We have time for some questions, if anybody has any. Shingo, over there. Sorry.
What is the theoretical limit of the quantum efficiency when you operate the system in a continuous way in an ideal parameter regimes? Because now you have 50% in some perfection. But I'd like to know the theoretical limit in ideal case.
So it's quite well described by our theoretical model. And over here, we attribute this mostly, so this efficiency, about 47%, is less than the cyclic efficiency, 73%, mainly because this is a continuous readout. So that is basically dephasing the symmetric mode continuously. So the next question is that what is limiting the cyclic efficiency? And that is mainly because of a finite T1 of our qubit, which is about 18 microsecond. So that is the reason that some of the times when we do those single shot, the excitation drops back to ground state before we actually, which we register, which we do not register in our efficiency measurement.
We have time for another question, if anybody has any. No? If not, let's thank Ali again. Yes, so now we have real-time detection of correlated quasi-particle tunneling events in a multi-qubit superconducting device with a talk by Linus Anderson, also from Simona Gasparinetti's group at Chalmers University of Technology. Take it away.
Thanks a lot. So great. So today I will be talking about real-time detection of correlated quasi-particle tunneling events in a multi-qubit superconducting device. So my name is Linus, and I am a PhD student here at Chalmers under Simone Gasparinetti in the 2020 Q lab. And apart from looking at quasi-particles, we're also studying, for example, quantum computing with bosonic modes, quantum thermodynamics, and quantum enabling technologies. But yes, quasi-particles. So yeah, you guys that work with superconducting circuits, you know that we all have to deal with quasi-particles, quasi-particle tunneling in one way or another. So for quasi-particle tunneling to occur, we first need to break some Cooper pairs. This can happen if you have high-energy phonons or photons in the vicinity of your junction. And this we do not really like because it causes decoherence in our circuits. But thankfully, there's quite some mitigation strategies that you can take in order to decrease this quasi-particle tunneling, which are more or less straightforward. So for example, you can improve your light tightness of your shield, for example. You can improve the high frequency filtering of your line. You can do all kinds of things to try to isolate your chip from vibrating. Or you can turn to more advanced on-chip techniques such as gap engineering or phonon trapping, for example. However, there is some certain type of quasi-particle tunneling which may be more severe, which are these kind of bursts of quasi-particles that we sometimes experience in our devices. And these are quasi-particle bursts where you see a great increase in the quasi-particle tunneling and which have been seen be quite catastrophic in some cases. For example, in many of the error correction schemes, for example, the surface code assumes that the errors are uncorrelated between the qubits, which is not the case for these bursts. So therefore, it's interesting to try to study these events more in greater detail. And you can turn to two main techniques, which is, for example, kinetic inductance detectors, or what we are using and many others in the superconducting qubit community, charge-sensitive transmon qubits. And when it comes to, there are a few common ways to detect these in superconducting qubits, the quasi-particle tunneling. You can use these coherent qubit operations to try to map the parity states to the ground or excited state of the qubit. That's one way. If you make the qubit slightly more charge sensitive, it's enough to just monitor the resonator and do direct dispersive monitoring of the parity states. Or you can turn to what we have been studying now for a few years, just coupling a qubit, a charge-sensitive qubit, to a waveguide. And this is what we are using basically in this study. So how this works is basically you couple a qubit strongly to a waveguide, and you just look at the parity states directly. So if you fixate on some of these parity states and monitor it in time, you can get these kind of telegraphic switching signals here. And this technique is quite fast because we couple it very strong, so it has a potential of being, you have a potential of having quite a small time resolution here. So what we naturally do to study correlated events, we add a second detector. And yeah, we can distinguish both parity states in both of these qubits. And now we start to monitoring these tunneling events in real time in both detectors simultaneously. So this is a typical raw data trace of what we see in our experiments. And in some instances, if you take a closer look, you see this rapid increase of the quasi-particle tunneling in either both or one of the devices. So actually we see three distinct categories of such events, where the first one is uncorrelated bursts, which is just that disappears in one of the detectors. So we can analyze a little bit of the statistics of these events. For example, the waiting time distribution. So if we just take a look at the bursts, we can see that they have a tunneling rate which is almost 3 orders of magnitude higher than the background, which is quite interesting here. And these bursts, they occur once about every minute in both detectors, which is quite similar to what other people have seen studying these burst events. So the second category, it's the correlated burst events. And this is where we see a quasi-particle burst in both detectors simultaneously. We can do some correlation analysis, so computing the cross-correlation between both devices, and we can see that we see a large peak for zero delay time and quite centered around 0 here, which tells us that these events are largely correlated. While if we remove the burst data from the overall data set, this correlation disappears and just correspond to this random Poissonian type of events. And if we look at the duration of these bursts, we can see that they, on average, persist for about 7 milliseconds in both devices, which is quite a long time. So, apart from just the bursts, in some rare occasions, we see, together with this quasi-particle burst, also a change in the offset charge. It's a little bit hard to see here, but if you look at the green trace here, you can see that the amplitude changes, and this coincides with this burst event here. And the offset charge, how this affects the this type of device, in general, you have a slow change over time. So this, if you would monitor these parity states over time, the separation between these states will slowly vary over time. But in some instances, we see a clear, distinct change, and this coincides with these bursts, essentially. And if you plot this in the IQ plane here, this will look like the two parity states moving further away or closer together, basically, which is just the fact that it's easier to distinguish the both parity states if they are further apart, essentially. But so if we take these offset charge shifting events and plot this together with an effective offset charge, we can see that these bursts, they occur very often here when we have a very sharp and distinct change in the offset charge of these detectors. And these events, they are much more rare, so we see them about once an hour approximately. And when they are correlated, that's about every 2 hours. So this kind of data kind of fits with this interpretation that we have some kind of high energy ionizing event that locally rearranges the charges and change the offset offset charge, and basically also creates a lot of quasi-particles due to the phonons, which is something that is being discussed as one main cause of these events. So, in summary, so we've been studying these correlated events across these two detectors. We've been distinguishing these three categories or regimes, where we see either non-correlated events, correlated events, and also these events which has this additional offset charge shift. So sort of a natural next step is to try to have more detectors, try to sort of spatially kind of locate where these impacts occur, whatever it is, and also potentially diving deeper into mitigation techniques such as the gap engineering techniques, phonon trapping, and so on. So that's a natural next step for us. And yeah, before finishing here, I just want to say that we do have some postdoc positions opening up soon. So please, if you're interested, visit the lab, contact us, or speak to us today. So with that said, thanks a lot for listening.
Great. Thank you very much, Linus. I think we have some time for some questions here, and we're already heading all the way up.
Hi, thank you very much. I think I might have missed it. What's your base layer made of?
Baseline rate?
So your base layer, the superconducting base layer.
You mean
the qubit material
yeah,
for the ground plane?
Ah, yeah, great question. That's very relevant, of course.
Yes.
It's silicon and
so
aluminum
the substrate.
junctions.
What's the superconducting layer?
Oh, it's aluminum.
Aluminum, cool.
Yeah,
Awesome.
yeah.
Thank you very much.
I guess for the quasi-particle burst rate that you see, does that match the recombination time that you would expect from aluminum in the material?
Oh, good question. Very good question. I haven't actually looked into it, but yeah, I mean, the material choice and everything matters quite a lot. I mean, depending on how long-lived your, for example, your phonons are in that material. So that's certainly a factor that you need to probably take into account if you want to mitigate it somehow.
Great, thank you. I think we have some time for some more questions, if anybody has any in the audience. No? If not, let's thank Linus again for the wonderful talk. Our last speaker of the session is Marco Gobo from University of Milano Bicocca, and he will be discussing transmon-based single microwave photon detection using Ramsey interferometry.
So hello everyone. So I'm Marco Gobbo and a PhD student at the University of Milan Bicocca. And today I will show you one of the work we are working on in our group. Especially we want to use quantum technologies for particle physics application like fundamental physics searches like axions. So just a first quick slide about how does an alloscope experiment works in axion field. Essentially, we use a 3D cavity cooled down at low temperature and exposed to a strong magnetic field, which is really important because if we have an axion halo and we want to convert this axion in another particle, we need a strong magnetic field in order to convert this axion into a microwave photon. And then if we are able to trap this microwave photon, we want to detect this photon through a detector. The usual way is to use linear amplifiers or squeezing techniques, but sometimes they are limited by standard quantum limit in the higher frequency range. So in order to elude the standard quantum limit, the idea is to use a single microwave photon detection. There is a strong motivation to go in the gigahertz regime because there are some motivation from cosmology that are trying to describe all the observed dark matter halo with just axions. So the takeaway is the fact that for amplifiers at a higher frequency, the scan rate decreases dramatically compared to single microwave photon detector. Then, for the detector, we are trying to use work that was already done 10 years ago in the Nakamura's group. So I would like to thank Shingo to be here today. And so just a quick overview, how does it works? Essentially, there is a transmon qubit, which is dispersively coupled to a 3D cavity. And the external coupling rate, the coupling between the transmission line and the cavity is fine-tuned to be equal to the 2 times the dispersive shift, which is really important. Then the qubit is initialized in a superposition state, and if there is a traveling photon coming from maybe dark matter or other sources, then the photon is reflected from the cavity and imprints a phase shift on the qubit state. And after closing your Ramsey protocol, you will end up in this entangled state between the qubit and your output mode. Our idea was, first of all, to start to implement a model that well described this interaction. And in this way, we started by modeling with the Molmer formalism, which is essentially based on the input-output theory, where you essentially design time-dependent couplings between fiducial cavities and your system. So how we do that? So first of all, we need a system, which is our two-level system dispersively coupled to a resonator, which is described by a standard interacting Hamiltonian. Then we want to fine-tune our parameters to match the matching condition that we want in order to imprint pi shift. And then we want to model our Gaussian input pulse, which will be a coherent state, which is described by the size of the coherent state and also the width of our pulse. And the last important ingredient is the output mode, which is coming from the dynamics of the system, which is essentially a filtered mode, which well described the output after interacting with the cavity. So first of all, we have all the ingredients. We have our input mode. Then we can try to define the time-dependent coupling between the first fiducial cavity and the system. We solve our system, and then we can try to model from the first time evolution the filter mode, which is our output. And then from this output, try to build our second fiducial cavity, defining this second time-dependent coupling. At the same time, we can have a look also to the population of each cavities. For example, this is for the output mode. As you can see, we start with a populated cavity, and over time we start populating the actual cavity that we have in our system, and also for our output mode. So in this case, we are populating cavity, and this is for the output mode. So this is our full framework, and we can ask, does the Molmer formalism describe the exact same physics that was observed 10 years ago? So first of all, we made a comparison about the efficiency. So as you can see in the first plot, we are plotting the qubit phase flip probability as you increase the size of your coherent state. And as you can see, we are able to model also the fact that the output mode is not only described by the vacuum state or the one-Fock state, but is populating also other transitions of our cavity. At the same time, we can have a look how does the efficiency change if we introduce an external internal coupling rate, and at the same time, since we are not working in a closed system, we need also to take into account some the coherence that comes from the interaction with the environment. So we need to introduce a relaxation rate and also dephasing rate, and yeah, coming back to our question, the answer is yes. So, but can we do more? Our system can be described by this schematic, and for instance, we can isolate and take the subsystem composed of the output cavity and our TLS. And we can, for example, have a look to the tomography of our system. So we have the diagonal correlation that enable us to perform a QND measurement. But at the same time, there are some off-diagonal elements that starts indicates the presence of entanglement. So, for example, we can try to understand how we can optimize the entanglement in the system. For example, in this case, we quantify the entanglement using the negativity, and in this case, we are trying to sweep the parameters, for example, for the system. So the coupling between the resonator and our transmission line, or between the resonator and the qubit, and try to see what is the best matching condition that we can try to achieve. And the answer is the fact that 2 chi should be equal to the external coupling rate. At the same time, we can try to engineer the input pulse in this way. So we can change the width of our pulse, for example, but if we change our width, we should take care about the line width of our resonator, because if the width in time is where the pulse is in time is in the time domain is very narrow, the contribution in frequency will be so big that we are not able to integrate the full pulse. At the same time, we can try to sweep the average photon number. And as you can see, as we increase the sigma and the size of our coherent state, we are saturating a negativity of 0.5, which is, for reference, the negativity that you may obtain from a Bell state. So since we have a subsystem which is entanglement, we have a qubit and the output mode, we can have a look, for example, to some measurements. What happens if we project our qubit in the ground state or in the excited state? So as you can see, if we don't project our qubit, we can describe that this situation with this on top of your right the Wigner function. But if we start measuring the qubit, so we start projecting the qubit in the ground state or excited state, we are essentially projecting also the output mode. In the first case, we are projecting the vacuum state, our weak coherent state, but if we project our qubit in the excited state, we are projecting the output mode in the first 1 Fock state. But what happens if we increase the size of the coherent state? Essentially, we are starting, see, there is some parity measurements between correlated with the state of the qubit. So if the qubit is a project in the ground state, we are establishing a parity measurement in the even states, or if we project the qubit in excited state, the qubit will end up in the output state will end up in out parity. At the same time, we are trying also to implement an experimental implementation using a planar version compared to the one that was already done 10 years ago. And in this way, this is a little bit more challenging because you have to fine-tune your external coupling rate just from your design, and after your fabrication, you cannot tune properly your external coupling rate, while with a 3D cavity, you can adjust mechanically directly on your cavity. Yeah, the first iteration, as we expected, gave us external coupling rate, which is very far from our target. So we started a few other iterations of fabrication in order to find a working device. So going to the conclusions, essentially we modeled a Ramsey-based SMPD using the Molmer formalism, which is really important. I want to stress out that in this framework, we have access to the density metrics of the output mode of the filtered mode that we obtain from the first dynamics. We validate also the framework with already existing results, and we optimize the input mode in order to maximize the entanglement we may have between the qubit and the output mode. And we generated also itinerant non-classical states, just projecting also the qubit in the ground state or excited state. And the next steps will try to implement from an experimental point of view, and also try to optimize the design to to achieve the highest efficiency and the lowest dark counts in order to implement this device for dark matter searches. In the end, I would like also to thank the whole collaboration and you for your attention. Thank you so much.
Great. Thank you, Marco. We have time for some questions if anybody has some in the audience. No? If not, let's give Marco a hand and thank all the speakers once again from this session. And now I think it's time for lunch, and we can wait until, or I guess we'll continue back at 2 o'clock with the final session of the program.
Okay, our microphone is live already. Very good. So people are still coming in. But we are now opening the afternoon session. It's the last session of this year's SQA conference. It's a session with 3 talks, 3 contributed talks. Your first program had 4, but 1 speaker wasn't able to join us, so we are now at 3. To all the speakers, I will, after 10 minutes, you have 10 plus 2 minutes. After 10 minutes, I will get up. And after 12 minutes, I will stand uncomfortably close to you. Specifically, even though the session is shorter, some people have to catch their favorite means of transportation to get home, so we owe it to them as a sign of respect to respect the time. With that, first speakers already wired up. The session is very technical, interesting for me as a theorist. It's about towards scalable quantum computing. And the first speaker, I hope I'm pronouncing the name correctly, is Fei Yan from the Beijing Academy of Quantum Information Sciences, about progress towards a scalable high-performance quantum computing platform. Please.
Thank you for the introduction, and thanks to the organizing committee. This is my second time in Gothenburg, and I feel very grateful to have the chance to catch up with some old folks and colleagues, and also met more new friends. And in this talk, I would like to split into 2 parts. First, I will quickly talk about our recent progress on the scaling efforts at the buckets. And then I will focus on a specific TRS problem, which we find is very interesting and will be and also informative. Okay, so we've been developing this 72 transmon qubit processor over the last few years. And this is a square lattice topology to be forward compatible with surface co error correction. And we use the flip chip architecture and also the tunable coupling architectures. And here we adopt all floating design with all the qubits, couplers, and resonators floating on the top chip. And so this makes the on-chip control line routing much easier. And so this is the so far the best performance over this series of devices. And we're happy that our average coherence time is above 100 microseconds, and the average 2 qubit gate fatalities are now below 0.4%. And we are looking into this iSwap type of 2 qubit gates, which we think that have a few advantages. For example, it's a simple pulsing, less leakage, and easier frequency planning, and eventually leading to higher gate fidelities. And also it's compatible to directional codes, which you hear from folks in Riverland yesterday. And we're not just limited to iSwap type of gates. And last year, we demonstrated that on the same hardware, we can do actually native arbitrary 2 qubit gates with this so-called Ashen gate scheme. And you will only need to add a microwave drive, single qubit microwave drive to the qubits during the iSwap interaction period. So there's no actual hardware cost to do arbitrary 2 qubit gates. And people were curious about when you're adding or not adding this microwave drive, does it hurt the performance? And here we show that we pick an array of qubits, and we did this side-by-side test between iSwap gates and the Ashen-generated B gates, and it turns out that the performance are similar. And just to remind you that the B gate is just a very unique 2 qubit gate, which you can use it to generate arbitrary SU4 operation with just 2 applications of B. And now I'll switch the gear to the TRS problem we have found on this 72-qubit processor. We all know that TRS is a notorious problem to us, and it's the TRS randomly appear in space and frequency, and more importantly, they fluctuate over time. This makes your frequency planning just harder. And on our device, we found a unique TRS. So here is a unit of 2 qubits and couplers. And when we measure the T1 spectroscopy of these qubits, these 2 neighboring qubits seems to have a TRS at the same frequency. Then at that time, we wonder, are they independent two independent TRS just by accident with the same frequency, or are they just a single TRS? Then we did some verifying experiments. First is to use the successive I-swaps to transfer excitation from 1 qubit to the TRS and then to the second qubit. It turns out, yes, you can see this excitation transfer pattern. This confirms that it's a TRS shared by 2 qubits. And to further eliminate this, there could be some random mode in our device. We observe, we continue to monitor the frequency of TRS, and it turns out this TRS frequency can do some random jump between 2 frequencies. So this is a very typical behavior of the TRS. So this is a shared TRS by 2 qubits, which are like a millimeter away from each other. How can a micro defect couple to 2 qubits distant with that distance? And we come up with the hypothesis that this TRS actually resides inside the tunable coupler that connecting the 2 qubits. This actually turns out to be very natural because the couplers are made in the same process as the qubits. So it is it's a reasonable guess that it will have the same amount of TRS as the qubits. So if the some TRS is strongly coupled to the coupler, and also the qubits we know that they are strongly coupled to the coupler, then the coupler acts as a tunable coupler between the qubit and the TRS. So it's very much like the tunable coupling architecture. And then just the interaction is mediated by the coupler now between the qubit and the TRS. And then you can, the maths are similar to the tunable coupling scheme. And you can simply calculate the effective coupling, which depends on the detunings and these coupling strengths. With this hypothesis, we tried to extract these parameters. We measured these qubit TRS spectrums versus the coupler frequency. And from that, we can extract these parameters. And we find out that the TRS coupling strength is around 30 megahertz, which is pretty strong. So, and because of this strong coupling, we can then do we can manipulate the TRS state by using the cross-driving technique by just driving the coupler at the TRS frequency. You can see here we can do very clear Rabi oscillations of the TRS, and we can then calibrate the pi and pi2 pulses and do T1, T2, Ramsey, and spin echo of the TRS. And it turns out this TRS is pretty long-lived with over 40 microsecond T1 times. And as I said, the effective coupling depends on the detunings between the coupler and the TRS or the qubits. So then we can do tunable coupling to further confirm this our model. And if we reduce the detunings, as you can see from the spectroscopy measurements, the avoided crossing between the qubit and the TRS becomes larger as you decrease this frequency. And also in the T1 spectroscopy, you can see that the oscillation becomes stronger when the TRS is resonated with the qubit, and also affecting a larger frequency spread. So this is between the first qubit and the TRS. And you can imagine that the behavior will be similar between the second qubit and the TRS, which is shown up here. Okay, so I think until here, there's a very important message here. So when you calibrate a large-scale device, do not overlook these TRSs, which are hosted by the coupler. This is actually very important. As you can think, when you do 2-qubit gates, you have to move the coupler frequency close to the qubit, right? And that will increase the coupling between the coupler TRS and the qubit, which could easily be overlooked when you do traditional T1 spectroscopy of the qubit when you before you planning your frequencies. Okay, then there will be some other extended experiments which I go quickly. And we further did some noise spectroscopy of the TRS for fun. So these are some this is a repeated Ramsey protocol and spin locking protocol we developed back at MIT many years ago. But now we just apply these techniques on the TRS instead of qubit. And with this, we can reconstruct the noise spectroscopy of the TRS. And this is the TRS noise spectroscopy. The spectrum extends over 10 decades from below millihertz to over a megahertz. And a few obvious observations that it is one-alpha-like, and also we see some bump features, which are indication of the incoherent TRFs, which are coupled to the TRS. Okay, and also we observe something interesting is that these TRS jumps not just happen in any, or not just always happen. These TRS random jumps only happens when the coupler frequency at specific values, which are very weird and interesting observation at the beginning. And now we are trying to explain this behavior with this new, what we call the multi-level fluctuator model, in which the coupler and the TRS and a multi-level fluctuator, they couple to each other. In this way, when the coupler matches the level spacing of the fluctuators, and it will assist the transitions between these interval between the interval transitions, and this causes this activated random jumps. Okay, if you're interested more, my student Yujia was giving a poster. Okay, I would like to thank first the people doing the experiments, Gao Yang, Zhang Yujia, and Xu Huikai. And this is project also supported by Dr. Yu Haifeng and our fab engineering team. And also we are a growing group at Buckis, and with 20-ish people. And I'm very grateful to work with my colleagues, and we share the same goal to make practically useful quantum computers. And we're also actively hiring, not just to Chinese nationals. And actually, Buckis has a very good international environment with quite some foreign researchers from Europe. With this, I would like to conclude. Thank you very much.
We have time for one or two questions, please. Yes, please.
Thank you for the great talk. I have a short question. So you mentioned these TLS. Are they cooldown persistent? So do you see them in different cooldowns, like the same TLS, same frequency, or?
Yeah, we did like 3 or 4 cooldowns. This TRS doesn't change between the first few cooldowns, but it goes away in the last cooldown. So, and actually we tried to monitor many other TRS. We find that usually the stronger the coupling between the TRS and qubit, and the more stable it is between thermal cycles.
More questions? One more, yes.
I was wondering if the T1, T2 times of the TLS also depend on the coupler detuning?
I don't have the answer out of my head now, but I believe I measured, and I believe there's no strong dependence, at least no strong dependence.
With that, let's thank the speaker again.
Thank you.
And we continue with, well, my program here on my phone just got shifted, but we also see it here. Massimo Borelli from Blue Force, who will answer the age-old question to us: what's the maximum density of control lines in a superconducting quantum computer?
Yeah, thank you. Thank you for the introduction. We'll try to answer that question. The answer is not 42, I can anticipate that. So, yes, I'm from Blue Force, and as you know, we do all the nuts and bolts, right? But we try also to do some more, let's say, academically flavored, sometimes research, and we try to answer this question that I'm pretty sure everyone else is asking here, which is, how do we scale up systems? And in particular for us, how do we scale up the cryogenic wiring? So you're all familiar with this. This is a bunch of coaxial wires, and they represent the state of the art. So this is the current approach that is very good because coaxial cables, from an RF perspective, have very good shielding, so you don't have to worry about crosstalk, right? And that's why most of the current literature about crosstalk focuses specifically on the QPU or around the QPU, because that's where you would typically expect crosstalk to arise. However, we cannot keep on scaling up forever with coaxial because they're semi-rigid, and for one wire, you essentially get one line. So you're limited by the density of, I mean, you only have the single wire volume that is limiting you in how far you can go. So the other approach that it's also currently under development at Blue Force is flex lines. So mechanically, these are less rigid, and in principle, you can put multiple channels inside one single FPC, FPC stands for flexible printed circuit. However, because of how they are, there is reduced shielding because you have these conductors running in parallel and they are kind of close to one another. So we need to start worrying about crosstalk already at the RT feed-throughs, basically. So, and we have to look into that, and we need to understand if that is something that will limit the scalability. So we have decided to cook up this little model here where we essentially describe the flex line using this term cryogenic signal delivery region, which is essentially a flex line that runs from RT to mixing chamber. And we try to describe it using the what is so-called coupled transmission line theory. We'll get to that in a moment. Then the second component is what we label generally space transformant. So this is some kind of component with an interposer that essentially reduces the pitch. And finally, we have the QPU. So now the key element in this description are these LC&CC parameters, which are the coupling inductance and capacitance per unit length that you have inside your cable, inside your flex line. So what happens is that essentially if you input a voltage at port 1, because of this coupling, you will generate a signal traveling in the adjacent line. And that means that both qubits A and B will receive some kind of signal. We use this formalism, which is called the even and odd mode, that basically allows you, in very simple terms, to calculate the output voltages given a certain input voltage, where this gamma E and gamma O, those are called the propagation constants of the even and odd mode. So what you're doing is basically the coupling is mixing your signals, and then it's what essentially generates the crosstalks. So now, what we did was, okay, let's take the definition of equal level crosstalk, which is, for us, we think it's really the quantity they should look at, because you know, the lines are very attenuated, so you want to know what is the signal leakage to the intended attenuation. And when you go into this picture, you see that you can connect the crosstalk directly to those parameters, LC and CC. The issue, though, is that how you connect those to the actual structure of your strip line, right? So because your strip line has a cross-section which is characterized by certain length, primarily the pitch between the channels and the width. And turns out that you can connect essentially those physical parameters to these more abstract per unit length parameters, LC and CC. And the way we did it, but you can also do it using FEM simulations, or it's essentially that we just measure, so we fabricated some strip lines, we measured them, and then we tried essentially to combine our theory with the measurements, and we saw that we had a very good agreement. So this is the Lfxt as a function of the distance between the lines at 3 different frequencies, 1 giga, 4 giga, and 8 giga. So we said, okay, that's good. We have a good way to describe analytically the crosstalk. So now we need to plug it into the 2-qubit. We go for a 2-qubit Hamiltonian model, but this model is completely general, can be generalized to many lines also. For just simplicity, but I have a slide if someone is interested. For now, we just forget about the space transformer. So let's just imagine that we connect our flex cables directly to the qubit. And we want to implement this Hamiltonian. So the green terms are the drive terms that you need for a single qubit. And then you have some kind of rotating wave type of coupling for your qubits. And we select 2 gates. The first is just single qubit rotations, and the second one is the CR gate, a bit old school, but it's definitely the most sensitive to this type of crosstalk because the qubits are quasi-resonant. So we wanted to look at the worst case scenario. And as you can see in both cases, you get the intended type of interaction or coupling, plus a term which is to the first order in the crosstalk, always proportional to the sigma y operators for the other qubit. So now the parasitic Rabi drives are included deterministically, and they depend directly and analytically on the parameters of your coupled transmission line. So we calculate the gate fidelities in this situation, and we estimate them using this average gate fidelity, where U is the ideal gate that you want to implement, and B is the actual implementation. And by doing the calculations, we're able to derive the fidelity for both the single qubit and the CR gate, first as a function of the wire design parameters. So this I minus and Q plus that you might recall also from the previous slide, they depend analytically directly on the parameters of your line. But then you can also essentially rebundle them together and rewrite the whole fidelities simply as a function of the actual crosstalk from your cable. And then when you look at the fidelities, the infidelities for both the RX and the CR gate, you will see that obviously, as you would expect, they decrease when the lines get further apart. At the same time, this is telling you that if you want to have 4 nines of fidelity for the CR gate, then you need to have that the distance between your traces in your flex cable must be at least 6 times the width. So how can we use these results? What can we use it for? So we go back to the original question, which is how do we scale up? So now we want to use this dependence, this D over W dependence on the fidelity to bound somehow the number of qubits on chip. We do something very simple. These are just to simplify the assumption. So we assume a square chip that has equally distributed interconnects. And we also assume that every qubit needs exactly 1 XY line. And then we say the number of qubits is approximately the perimeter of the square divided by the distance, by the pitch of the interconnect. And now we want to bound D1 mean to the fidelities that we calculated earlier. And when we do that, we find that for this type of very simplified scenario, we're able to draw these lines that are basically telling us, okay, if you want to have 3 nines on fidelity on the CR gate in a chip that is like 3 centimeter times 3 centimeters, only, including only the crosstalk from the flex line, you cannot go above 270 qubits. So now, this is some kind of fundamental limit on the RF manipulability of your qubit that comes essentially just by the crosstalk in your lines. And this is important to us because, you know, as you may imagine, customers are always like worrying about the heat load per qubit, as if that would be the only very limiting factor. But we want to show that actually it's a bit more complex than that. So I'll come to the conclusion. So the way we see this work that has been recently accepted in PRL, should be published next week or the one after, is that we try to find a unifying framework to connect a quantum model to transmission line theory. And from a practical point of view, gives us a physics-grounded fundamental limit on how the wiring density will govern the crosstalk in the lines, and can help us make some informed choices when it comes to wiring design. And the long-term idea is that this will give us a sort of like a blueprint to scaling up quantum computers. And we're at the moment investigating how to apply these to tunable architectures and also how to do randomized benchmarking within this context. And I would like to thank the quantum team at Bluefors. Thank you for your attention.
Thank you. Thank you very much. Talk is open for discussion. Maybe let me start with a question. I don't see anybody, but I'm also many people. Whenever I see somebody claiming a fundamental limit, I have a Pavlovian reflex to beat it. So I'm wondering how predictable is your crosstalk? So if I come up with a very well-known crosstalk model, I could use optimal control to do something about that.
Yeah.
So is the predictive power of the circuit parameters really high, so I can do something about it?
Sorry, no, I would like to.
And the stability?
Yes. So this. So we this crosstalk model here that gives you. It's not something that we invented. So this is textbook. What we did is that we extended it to multiple lines. And yeah, the power, let's say how predictable, it depends on the structure. For strip lines, it works very well. For microstrips, not so well. Because the assumption is that your fields are TEM, at least to a good degree. And this is always the case with coaxial, right? With strip lines, it's almost always true, but with microstrip, you start seeing deviations. I'm not sure about coplanar waveguides. We haven't applied it to that, but it's very suitable for at least what we were interested in. So,
okay, thank you, Johannes.
Yeah.
Thank you for the answer. Now there is a second question.
Okay.
I should be less terse.
Thank you for the insightful, high-level, like useful high-level analysis, which like fundamentally answers some questions. But one of the assumptions you made was that you are using these microstrip lines, and
strip lines, yeah, exactly.
In the same form factor, with the same technology, you could easily have ground lines as well in between to add like a little bit of shielding in between the parallel microstrip lines. Yeah, I guess you can also add some vias to.
Yes. I mean, okay, but those
you can make then
at that point it becomes a more RF engineering problem. Okay, so what we wanted to do was, like, let's say our idea is to not just rely on engineering, but we want to see if there are like physics grounded arguments that we can make about scaling. So that's but yeah, for sure you can add vias, you can add all those, but those are like these are design features. that are obviously like proprietary. But yeah.
And the same concerns apply to the lines on a QPU, right? So the number of QPU lines can easily increase if you have a flip chip with some interfunction between.
No, exactly. But what I'm saying is that we are trying, let's say, the way we see this work is that we try to start a conversation about the fact that scaling up can be a physics problem and not just an engineering problem.
Thank you.
So that's the take.
Thank you.
Thanks.
Thank you. Are there more questions? So now let's thank the speaker again.
Thank you.
We come to the final presentation of the session. That is Connor Shelley of Oxford Quantum Circuits, design and operation of wafer scale packages containing more than 500 qubits.
Okay. Right. Thanks, everyone. Thanks to the organizers for this great conference. And I'll be the last technical talk, I think, and then we'll all go home. I'm from OQC. I'm going to talk about the design and operation of large-scale devices and packages. So we've developed monolithic 3-inch wafer devices and create a package for 500 qubits, and I'll show you the results of 100 of them. Before I start, just to give a little bit of an introduction to OQC's unique implementation of a qubit. So we make what we call coaxmons, which is a coaxial transmon device. This puts a qubit cell on one side of a wafer and a readout resonator on the other side of the wafer. The advantages here is we can have our control and readout lines in the Z direction. We don't need flip chip bonding, wire bonding, air bridges, etc., and allows us to scale this architecture. One quick call out, and then I won't talk about this again in the talk, is what we call our daimon. This is a dual rail implementation of our coaxial qubit. The point I want to make here is that everything I talk about in terms of the scaling arguments can be applied to our daimons. So we can put daimons on these wafers in the same packages. Here's a picture of our wafer. So it's a 3-inch wafer, sapphire wafer with aluminium devices and aluminium oxide junctions, sitting in the package with the top off, obviously. There's a number of considerations that we'll go through that are important for this kind of packaging. I'll talk about some of them in detail, and I'll talk about some of them just with sort of single words near the end. So multiplexing, the RF modes in such a large cavity, some of the lost channels with both the devices and some of the materials that we're using in this package. The mechanical motion, now you have something quite large and you have thermal contraction, differential thermal contraction between different materials. And then the cryogenic payload, I'll just say one sentence on at the end. Here's a profile picture of our package. So we have an aluminium package, a base and a lid. We have a PCB, which I'll go to in a bit more detail. A spacer, which I won't talk about further, but this is just an aluminium spacer that allows us to accurately set our coupling. So we can change the thickness of that spacer to determine the coupling to our qubits. And then finally, the wafer. And the pillars. I'll go into that in more detail. I'll talk about the PCB first. So rather than put multiplexing architecture on the wafer itself, we take the multiplexing off of the chip. So we have a PCB multiplexer here with these 9-to-1 patches. We have 9-to-1 multiplex lines and a Purcell filter built in. That allows us to just scale this PCB patch across a full PCB that can scale as large as we like. And we just place this on top of our wafer that allows us to have 9-to-1 multiplexing of our 500 qubit demo. We have a really big package. So that means that our box modes are quite low frequency. So if we look at the bare package, we will have a fundamental frequency of 2.5 gigahertz, something like that. Further modes in this package will cover quite a wide range. And annoyingly for us and everyone in this room, transmons and our readout resonators are within these frequency bands. So we need to do something about that. Now talking about the pillar, this is one of our box mode mitigations. So what we do is we make holes in our wafers. So we drill holes through a sapphire wafer. We have an array of metallic pillars that short between the base of our package to the top of our package and interrupt these box modes. So you can see a picture here. This is a zoomed in picture of our wafer. You've got all of our coaxium devices. If you've got good eyes, you can see the pin of the readout line just underneath that poking through. And then the pieces of metal that are coming through, these are aluminium pillars that are coming through drilled holes or drilled apertures in a sapphire wafer. The effect that has is this. It allows us to push our fundamental mode out of our qubit frequencies and our readout frequencies. So it allows us to really reduce any possible issues with box modes, crosstalk issues, spurious connections between these. Again, we have a big package. So we now have to care about thermal expansion or contraction of various different materials. We have a PCB, we have this spacer, we have the sapphire itself, we have pieces of aluminium coming through. So we've done some modeling to check that if we put this thing together and we cool it down, that it's not going to burst itself apart, it's not going to break the wafer, it's not going to damage the PCB. So we see across the total wafer about 120 micrometers of sort of movement from piece to piece, which will mean that in the future we have to be quite careful with our matching of thermal expansions. Some results. So 500 qubits on the wafer. We connected enough to measure about 100 of them. That was just due to line limits in our cryostat. And we just connected a subset. We didn't choose anything in particular. We just placed our multiplexer connections down and measured. So all the data on this this slide, it's the same data, our T1 and T2 data, just visualized in different ways. So when you have so many qubits and this large wafer that you can read out, you can start to visualize things in different ways. So you can start to look at the multiplexer to see if you have issues with the multiplexer or if there's different performance on line to line. You have your typical histograms of T1s and T2s just so you can see the range of coherences we have. And then you can start to interrogate spatial variations over these large distances. So rather than just seeing if you've got some change from device to device, is there something you're doing in your package or your fabrication or anything like that that might have a spatial component to it? Some simulations I won't go into in detail, but we've done some finite element simulations of the devices that we make, so our materials and our substrates. That suggests that actually the coherence limits from this work are from the devices themselves, so from our substrate, from our metal. The point here is that our package is not a coherence limiting package, which means it can be used as a coherence metrology tool. So we'll be able to test out fabrication and materials work, fast iteration on very large numbers of qubits. As an example of why this might be useful, or at least why we think it's very useful, typically when you're measuring qubits, you might look at your median number, which probably gives you a reasonable idea of your process. You might look at your maximum number and stick it in a paper as a really nice high number. And not many people are looking at their minimum numbers. So as you're making larger and larger QPUs, you want to make sure that your poor qubits are being improved and your processing is actually bringing up this tail of poor qubits. This is statistically quite difficult to get with small numbers of devices. So what we've done is we take our as known coherence numbers that we've just found, these 100 plus T1s and T2s. We do some sort of bootstrapped random sampling to see how many qubits do you actually need to measure to get an accurate representation of your median, your minimum, and your maximums. You don't need many to get a median, so you can take small numbers of devices and get a reasonable estimate of a median, which probably gives you an idea of your medium processing capability. To find max, you don't need that many, and I'm not sure that max is that important apart from really pushing the limits of what you can do. But to find your minimum, you need to actually measure quite a lot of qubits to reasonably find this. And if you're measuring small amounts of qubits, you probably aren't getting your minimum number, so you don't really know what's limiting you in terms of your poorest qubits. So in summary, we've developed large wafer die fabrication at 3-inch, a package that allows us to scale this. So our future QPUs will be monolithic wafers using all the tricks that we've used here with our box mode mitigations, our multiplexers. We show that our package doesn't reduce our coherence, or doesn't reduce our quality of our qubits, and that the scale of this becomes a metrology tool for us. So this is now being put to work as a materials and fabrication feedback platform for our qubits. There's quite a lot more in the paper if people want to have a look. So we've done some cryogenic payload modeling to see how many qubits can you actually fit into one fridge. We could measure all 500 if we'd had the lines. Some readout work, some temperature work we've done in there, as well as quite detailed loss simulations that I haven't gone into of the package itself, where we're looking at the conduction loss, seam loss, etc. And I think, like many others here, OQC is hiring for lots of different roles. Please look on our website and come join us.
Thank you very much. And I see the first question here in front already.
Nice talk. And so do you have any like experimental result on the box mode? I can see from your design, it's pretty like intuitive, like you push the frequency higher, and did you do any measure of the box mode frequency like in your device?
We don't see it in this. We've got a number of test devices where we're doing this, where we have like an antenna port that we're putting in to see what the box modes are. Maybe one thing to say, not quite answering your question, but to say something else, is that this this pillar mitigation that we've got scales up to very, very large wafers without changing the pitch of the pillars. We just need more of them, but it's quite a nice scaling route to keeping the box modes away.
There's another question over here.
Yeah, very interesting, thanks. I was wondering about the thermalization properties of your package. Do you see an improvement in coherence numbers as the cryostat keeps cooling down, and what's the time scale over which they settle?
No, we don't see any changes over time beyond normal fluctuations from TLS and things like that. We got very nice temperatures of our qubits, something like 34 millikelvin. But that was done at the end. So that was at the end of a 6-month cool down. So maybe your sort of long tail thermal processes have frozen out by that point.
Is it something that you believe that you should address, improve the thermalization, or?
Say that again, sorry?
The thermalization, do you think it's good enough? You don't need to change materials or look at it differently?
We think it's good enough at the moment. Yep.
Thank you.
Are there more questions? Yes, one in the same corner.
Thanks for your talk. Very interesting presentation. So I'm curious, since it's quite specific implementation, quite different from other approaches, could you maybe say something about the yield of your device?
Of the yield, did you say? Our yield of our device is very high in terms of can we make the qubits and do the junctions exist? This will be around 100%. Give or take, Our junction spreads are typically very good over this wafer size as well, between 2.5% and 3% of junction resistance targeting over a 3-inch wafer.
Thank you. Are there more questions? Yes, one more. Chris?
Hi, thank you for the nice talk. When you're talking about trying to do the statistical bootstrapping for trying to figure out what your minimums are, do you have to take into account, say, the time variance that you would get over normal drift of T1 in a qubit? How do you kind of account for individual qubit drift in terms of its T1?
Yeah, okay, we didn't take that into account for bootstrapping, but in terms of what we're measuring there, can I go back? Yes. With these qubit T1 times, so every one of those T1s is taken, there are 100 measurements, and then that's a median of those measurements. Typically on each line it will be interleaved, so multiple qubits being measured, T1 swap qubit and keep going around. So you are having some smoothing out of your temporal fluctuations in that, and so it's a median of medians, and then we're bootstrapping from that.
Okay. No more questions, so let's thank the speaker and all session speakers again. Can you leave me on for a moment? Because I think, the closing is, of course, done by the organizers. The organizers, you see are Chalmers University of Technology, scaling at IQM. And I think, as a humble participant with gray hair, I would like to thank them to do this massive undertaking of doing it locally, but also providing the continuity. 7 and 8 years ago, when somebody asked me, can I come to your annual Superconducting Qubits conference? I had to say, we are too lazy. We don't have one. We hijacked the March meeting. Now we have it, and I think it's now becoming a continuous thing, and specifically also for a company providing this continuity is very unusual. So I hope you all join me here in thanking the 3 organizers for making this a truly enjoyable experience.
Yeah, you hear me. Okay. I come up here to say thank you again for coming to Gothenburg. It's been really fun having you. It wouldn't have been possible without each and every one of you, but I think that there's one person that we need to thank even more, Stefan, who has done this 5 times now. I've only been, this is my 4. 4. Yeah.
Okay.
There's coming a 5th. Spoilers maybe, but I've only been this 1 time, but I've heard from many others that this is the best edition yet. So a warm applause to Stefan. And yeah, we thought we were gonna give a nice present to you from all of us as well.
Thank you very, very much. I mean, good that I brought all the lanyards here by my luggage, so I've now a lot of space. I was close to paying over luggage at Lufthansa, and now I'm like, I think I've only 8 kilos or something. So I have space. Thank you very much.
We'll check next year if you finish that.
Oh, okay, I need to say something. Yeah, I mean, I want to thank all of you for staying with us, and especially I want to thank all of you who supported from the beginning. A lot of companies here are actually on there that from the beginning believed that we can organize a very, very open community event. And I have to share this one story that happened yesterday evening when all of you left and I had to sign the bill for the drinks. And by the way, we did not reach the drinks limit, so that's the challenge for next year. There was this barkeeper, and I'm allowed to tell his name, and maybe he watches the stream, I don't know, Dante. And first we were speaking about the 7-1 game in Brazil. Obviously, it was more the happy topic for me than for him. But what he said was he is doing a lot of events there, and this was by far the most friendly, most open crowd they had there. He felt really the excitement of everyone's when he was speaking about their research. He said he didn't understand any word, but it sounded nice. And that he felt that all these people are knowing each other for years, if that's correct. And I think I had to say no. I guess most people have only met this year. So I think it's really, really great. So thank you for making this such an amazing event, because only you guys make a conference a truly great event. Otherwise, it's just a session of continuous talks. So, and the thing is, we obviously all do it again, and we got the question, where will it happen quite often? But before that, there is something else we still need to do. We do have, and that's why Frank is on there, and we also need Robert, we do have still the poster award to give out. And as you that was actually a tradition, not a tradition yet. I think Amber told us it needs 3 times to be a tradition in Delft, and Christian from Delft started it. So we have one poster award for Wednesday, one for Thursday, and then the community award. And I would hand over to Robert to let us know. And actually, we don't even know if those people are now in the audience still, because we've not informed anyone in advance. So it might be a surprise to those people as well. Yeah, who's the first one?
Okay, thank you. So this is from the first poster session on Wednesday, I think. There were a lot of great, very interesting posters, so thank you everyone for giving those. But one really intrigued us, and this is the one. The motivation goes like this. A novel display on how quantum computing could be used to reveal new exciting fundamental physics combining both theory and experiments. And the poster is simulating SU2 Young Mills on Foxonium qubits, presented by Klaus Ligner. Maybe are you here, Klaus? Ah, here he is. So, congratulations. Well done. Very nice poster.
Thank you so much.
Want to say something?
Thank you so much. And by the way, this poster has theory and experiments and wouldn't have possible without a great team at my institute at the WMI. So thanks to all of them who are still in the audience.
Thanks.
Okay, so then there is a Thursday poster, and for me as a theorist, I have the honor to present something I could poster to somebody who does work that I could truly not do myself. It is on fabrication. Fabrication I do with good results in the kitchen on the weekend. And the poster title is also haute cuisine of sample fabrication. It's subtractive CMOS compatible qubit fabrication and 3D integration technologies for scaling superconducting quantum processors. And the award goes to, we do not have recorded the first name, to C. Moran Guizan, whose name I'm probably also mispronouncing. So C gets an award. Please come up. So, congratulations. Here it is. Are we taking any pictures? You want to say something?
Yeah, thank you so much. So this poster was kind of a last minute thing because my supervisor is on holidays and I had to. And I got a title and of course the work of all my colleagues at the Fraunhofer EMFT in Munich. So of course this is a team effort. Thank you very much.
And there is one last poster, one last poster award, which we tried this year for the first time, and then it bugged. So you could vote in the app, and I had spent the last 45 minutes using Claude to reconstruct the actual votings because I removed 2 posters throughout the week, and that shifted all the voting. So shoot, it was I was sweating that it was still reconstructed in time, but it did, and we have. I have not noted down the poster in title, actually, only the number. So it's P69 and has 36 votes. Well, that's what my script spit out, and I didn't write down the title, but I've looked up the name. And I would like to ask Saya Schöbe on a stage for the last award. Do you want to say something as well?
Okay, so, I mean, again, I would like to thank my institute for supporting the poster, but I would really also like to call out Alice and Bob because you were my main competitor, and I really loved to have this opportunity to have this friendly relationship with you. And I really enjoyed the time spending talking to you, bantering, and I hope to see you next year. And maybe you should try a little bit harder. So.
I have to say it was really, really close. Second spot was actually Alice and Bob's poster, and it was, I think, like 2 votes or something in the end. It was really, really close. I still need you 3 guys, please, because we still don't know where we are going or where we're heading in 2027. Please check what you have in front of you and tell us if you find any hint where this could be. Oh, how could you have spotted that? So it's pretty obvious, I think. It says something about espresso. So I think SQA is known for good food, and there are a couple of countries known for good food, but this is one of them. So we hope to see you again next year. And the last thing I would ask you for is the next toast should really go on Philip and Lisa for not only the party yesterday, but also the after party I heard. From that, we close now. This is the end for SQA 2026. Organizatorical advice, please don't stay outside for too long here because we need to deconstruct all the things. So if you want to mingle, please downstairs where you don't block the dismantling. Well, and then let's hope that we all see us next year.